So the person told me that it was fine to stream, so I decided to get this stuff because I think it's worth it for the price. I can also train command line if I have time. I think I might stay with this for 2 months or even more, depending, because there are other things that actually look like they're gonna be very useful. I always wanted to learn. I, I I was gonna study the command line for the tests, the for the Turing tests, but I ended up not doing. But I think doing the like this is gonna be much better because you're actually practicing the commands. There's also VS Code here and PyCharm, which are gonna be very useful. And it's something that I'm delaying. I always think about, especially on PyCharm, for certain types of things that I'm gonna look at that later, but I never looked it up. Look it up. So I think those are probably enough to make up for the price, and I think it's worth it. So PyCharm, VS Code, Vim, and the command line is probably more than enough to make this worth. And then I can train Emacs as well. I think I'm gonna move to Emacs at some point because I think you can use Vim inside of Emacs, and Emacs is more like a complete text editor, as far as I understand. It's more like an IDE, and Vim is just the text editor. There's also Git, which is gonna be useful. Git command line. These ones I don't think I'm gonna do, but they're probably useful, and this one's useful as well. So I think there are a bunch of, just these ones are enough, probably. So I'm gonna listen to some music and do this for some time, and then I will start the project here. And I'm gonna put it on the stream because it doesn't matter that much. Oh, now I can see the people that followed on OBS after the update. Hmm. The only issue I have with this so far is that it doesn't say. Some of them are kind of difficult to know when I'm gonna use them, but I can just look it up later. It's a lot easier to learn here and then look it up and then I can practice. So it's a lot better to learn than to just look it up. I think I learned very fast actually, the beginning, the basic ones. So if I do this every day, probably for 2 hours or something like that, I'm gonna pick up every uh, all of those that I just talked about really fast. Change char and return to command mode. Bandit and this one I already know. Change Rust of current verbs. And then they mix some of the previous ones with this one, which is nice as well. Oh, this one is going to be very useful. Insert new line below. This is something that I've always think about, but I didn't know what to do. To replace modes. I know that V or caps lock V is visual mode, and you can use that mode to copy stuff and paste. Or actually you select lines with that mode. But this one I never used. Oh, it does change here. Interesting. Ah, I think I get it. So it just replaces everything instead of... Ah, very interesting. Yeah, this seems like it's gonna be very, very useful. You just code like this. Yeah, the only downside is if you wanna write something that takes more characters, but yeah, really interesting. Okay, let me go back to this. Delete words. Ah, interesting. Nice. It feels like I'm not gonna be able to... It's probably gonna be like an exponential curve, because it probably follows the Pareto distribution. The first words are more important, the fundamentals, and then as you learn more and more, it gets harder and harder. And then it takes more and more time to learn, because I have to keep track of everything else that I learned. So it's probably gonna be exponentially slower as I get to more and more commands. But I think it's fast enough to make it worth it. Let's see what the append is. Okay. So A just switches modes and goes to the end. So I can press like this in A and does the same thing as shift in A. Okay. Change share and return to command mode. So this one probably returns to the other one. So it only changes the thing once you press the key. I wonder, let me see if it works if I press more than one. Interesting. It doesn't work. So it only changes one letter, I think. But maybe it's useful if you select. Let's see, V, then R. Ah, interesting. So when I select and I press R and then I press Enter. No, when I press a letter, then it substitutes everything for the letter. Start new line above. Ah, nice. Yeah, these ones are very useful, I think. At least it feels like it's gonna be very useful. But maybe I should remember everything correctly. Inserted starter wire. Nice. Yeah, that makes a lot of sense. I like the way they did the progression here. Is there a new line above? Yes. Okay. So the lower one inserts. The caps lock one inserts above, and the other one inserts below. So normal O inserts below, and the caps lock inserts above. It's kind of difficult to remember, but I think some more training and I'm gonna be able to. Do this method. Fuck. And maybe I'll do the hide one, because I think with a little bit more time I can remember, but the thing is just too fast. Fuck. I'm confusing the replace mode with the other one. There we go. Oh fuck. Oh, fuck. It's kind of fun, to be honest. Feels like a game. Oh, shit. I think I'm gonna do this until the music gets showed just a song that I don't like. I don't know this mix that is playing, so so far I'm enjoying it. And there's still half an hour left, so I think I might do this for another half an hour. And then start the other stuff. I think I'm gonna eat soon as well, in 17 minutes. I wonder if I should try to go as fast as possible to the end and then come back in the previous levels. So I get a sense of all of the commands at once and then go back, but I think that might mess me up. But at the same time, I think the most important ones should take a long time was the first ones, which are the fundamentals, and I think I got them correctly. Oh, fuck. I think this level is more engaging than the previous one because there are more commands, so it gets harder. The other one was kind of tedious to do. Maybe it's because I did it so many times as well, that eventually it just gets boring because it's not a challenge anymore. That's why I'm thinking about going faster through levels. So once I start getting bored of this one, just move to the next one. Maybe it will help me remember everything faster. It's also, I don't know how well I'm gonna be able to translate this into the actual coding, because I don't know if I'm gonna remember which commands to use at which time. And I think the beginning ones are easier when it comes to that because you're just doing basic stuff, but these ones might be harder to do that. Hey man. I'm glad you let me do it. Thank you. I felt that it's better to ask because you never know. It's paid content, but I don't think it. I think the value comes from the training, so it makes sense. Yeah, no worries. Fuck. Thanks for following. Shortcuts. Who? Oh, you're actually tipping me? I don't usually see this stream because I don't like seeing myself. So I look on the OBS, but yeah, thank you. Thanks a lot, man. Which one? I think I only tried this one. I did... I think I did probably thousands of times the first one. And that's why I decided to do the other one, because I thought it was really useful. And then I just did this practice to learn, but oh, here. Oh. Oh, interesting. Beginning of the line. It's kind of difficult to design in a way that you can use it, right? I think that's, I mean, if you could do that, I think it's probably really hard, but I was thinking about, because the initial commands were easy for me to translate into VS Code, but as I get more in depth, I'm not sure how I'm gonna be able to do that, or I haven't tested yet. The beginning ones were very easy, but because the more uncommon something is, the harder are the chances that you're gonna actually use when you're coding. So, but that's a very, very difficult thing, because how would you train that? Like when you should use each thing instead of just learning the commands. And I'm not sure if it's possible to do that, but a GIF on the commands of the command. You're saying when I press here? Oh, it shows the animation. Nice. So if I wait, it shows. Okay. Yeah, that's really interesting. I mean, it has for all the levels? Or depends on the level that I'm at, I guess. Yeah, this seems to be for the current level that I am. Yeah. Nice. But I think it's really good. This level is a lot more engaging than the previous one as well. But I guess that's just... there's nothing you can do about that. So because this one is more engaging because it has more commands. So it's still... it's difficult enough that it can get me to a flow state, let's say. The previous ones were just the basic commands, so after a while you get used to it and then stops being so... it starts getting boring, but I think it's just part of the process, so... I'm excited to see the other ones as well. I think they're gonna be really useful, especially the terminal ones, because it's really hard to learn the terminal just from watching videos. You ended up forgetting everything. So I'm really excited for that. This one will train you on the commands you miss most often over time. Oh, nice. Yeah, there we go. I would like the... I'm not sure if it works. It would be be nice if I can get these modes forever. That is also something that I think would be cool. I mean, I can go back to the other one, I guess. That's fine as well, but because what I like to do is to train a bunch of times. I don't know what I'm gonna do now, but I think it would be interesting to be able to just spend as much time as I want on each one, so I can train for thousands of times and really remember. But it's not a big deal as well because you can just do it here. Yeah, no worries. Yeah, sure. Thanks a lot for the tip, man. I really appreciate that. I think I'm gonna do something to eat as well. Yeah, thank you, man. See you. So I'm gonna go do something to eat, and then I think until the end of this stuff, there's still 15 minutes left, I think. So I'm gonna probably do all the levels. I'm gonna do the other levels, and then I'm gonna go back to this one later. And I think I'm gonna do it like this: advance all the levels so I get familiar with all the commands, and then go back to reinforce the previous ones and do on a cycle. So until I learn everything, and then after the music is done, I'm gonna start with the tutorials. So I'll be right back. Oh, actually, I just remembered that I have to see the diet stuff. I gotta see what I'm gonna eat. Okay, so milk. And I also have to write it down. Oh, it's actually true. And milk. Okay, so this is gonna be in 5 grams. I'll be right back.
another stream. Today we're going to try something slightly different than we've done in the past. Understanding, because if you understand how variables work and you understand how mutations are working and how it is represented in assembly, then it's going to be much easier for you to get some of these larger concepts such as ownership and borrowing, etc. Because you're going to understand exactly what's happening underneath the hood, and you're going to understand what the difference between a stack and a heap is, and how that's represented in code. So with that being said, let's write some Rust code, and then let's look at how that looks like in assembly. Okay, so first thing we're going to do is create a new Rust project. I'm going to do that with cargo by just typing in cargo new Rust assembly play. So we'll just do that, and then that's going to scaffold up our code, and then as you can see, it's created a directory, and my code is there. So if I type in code dot, then it's going to open up this new scaffolded project in Visual Studio Code. And now what I'm going to do is I'm very quickly going to write a brand new function, which is just going to do something a little complicated. It's going to do some multiplications and some additions, etc. Assign to some variables, and then what we'll do is convert that into assembly. Alrighty, so the first thing we're going to do is initialize some variables. So we're going to have two variables, one called num1, and I'll set that equal to 10, and another variable called num2, which I'm going to set to 20. Then what I'm going to do is multiply the two numbers together. So we will set result 1 equals num1 multiplied by num2. Then what I'm going to do is I'm going to do another calculation. So, and this time I'm going to take num1 multiplied by num2, and then I'm going to multiply that by 2 again. So I'll put num1 times num2 multiplied by 2. And then the last thing I'm going to do is do result 3, and that is going to be equal to result 1 plus result 2. For all of you trying to do the math at the moment, the math is not that important. What I'm trying to do is just have some multiplications and some additions so that when we look at the assembly language, we can see some of the optimizations that are occurring underneath the hood. So last thing we're going to do is going to print out result 3. So we will just do print line result 3. That will do. I'll add a little message of the value of result 3 is whatever the answer is. So that's our very super simple Rust program. What I'm going to do now is switch back to the console. We'll just clear this, and then if we do a cargo run, we should get an answer. And as you can see, the value of result 3 is 600, and that makes sense because what we're essentially doing is 10 multiplied by 20, which is result 1, so that's going to be 200. Then what we're doing is num1 multiplied by num2 multiplied by 2, so that 200 is going to then be multiplied by 2, which is 400. And therefore, what we're now doing is taking result 1 plus result 2, so result 1 is 200 plus the result 2, which is 400, which is equal to 600. So well done, Rust, you are a good mathematician. So how do I emit assembly? Okay, so if we look under the your target debug folder here for a second, one of the things you'd notice is you see the Rust assembly play, which is the executable that we generated. In fact, if I were to open that up in my console for a second, so let me just open up a new tab. And then if we go into target, and then we go into debug, and then if I were to run Rust assembly play, you can see it executes the code. Now if I come back in here, what you're going to see is lots of output files, etc. So what Rust is actually doing underneath the hood is it's going through a build process, it's creating all these various object files, etc. And then what it's going to eventually do is take that and then convert it into the executable. What I want to do in this case is part of that build process, I want it to actually emit the underlying assembly, so I can take a look at that. Now how I do that is if I come back here, and then what I'm going to do is just type in Rust flags equals, and then I'm going to do dash dash emit ASM. So it's basically saying I'm setting a Rust flag. I'm going to want it to do emit ASM. So go generate me some assembly for the code that I've written. And then if I just do a cargo build. So now that it's done that, if I come back into Visual Studio Code for a second, and then we come back into that depths folder for a second, what you're going to notice now is generated a .s file. And if you look at, have a look here, we'll just ignore this for a second. You can see it's generated a load of assembly. And then if I were to scroll down or even just do a search for main, you can then start to see some of the code that's been written. Now in this particular case, this is written in ARM, because if you think about this for a second, I'm running this on an Apple Silicon M1. So I don't really want us to look at ARM assembly. I want to be looking at more of the Intel-based assembly, because that's what most people are going to be running on their machines. It's also a little bit simpler for us all to understand as well, and a little bit more standard. So what I'm going to do now is I'm going to cross-compile this into Intel for my Mac, and then therefore it's going to be more like what everybody else is going to be able to see. To do that, let me just clear this. The first thing that I need to do on my machine is I need to be able to set the target so that I can target x86 rather than ARM64. So I'm just going to type in rust up target install x86 64, and we'll put Apple and Darwin. If you're not sure what targets you have on your machine, you can just type in actually rust up target list, and then that's going to give you a list of all of the targets on the machine. So you can kind of see there's things like WebAssembly WASI, there's WebAssembly unknown. So because of course Rust, and then you can see there's ARC64 Apple Darwin, which is what it was generating earlier. So if you're unsure which target that you've got, you can just type in rust up target list, and then you will see what type of targets are kind of available. And that's actually super important because Rust can obviously compile to multiple build targets. It can compile to WebAssembly, it can compile to Intel, it can compile to ARM. So you know the assembly that it will emit would be different, etc. for what you're building for. Now, so in this case, we're going to be building for an Intel machine, so I'm going to cross compile to that. So let me just clear that, and what we will now do is I'm going to do a cargo build dash dash target, and now I'm going to use that target that we saw from the rust up target list. So I'm just going to type in x86 underscore 64 Apple dash Darwin, and now it's going to compile that for the Intel-based machine for an x86. So again, if I want to run it, I can do a cargo run dash dash target x86 underscore 64 Apple dash Darwin, and then it will run. And then it says the value of result 3 is 600, so it still works. And that's because underneath the hood, even though I'm running an ARM64 machine, it's an Apple Silicon M1, because of the magic of Apple and Rosetta, etc., it's able to run x86 code anyway. So that's all kind of good for my machine. But more importantly now is that when I emit my assembly, then what I'm going to be able to do is look at Intel-based code. So let's just clear that. And then what we're going to do now is we're going to run that Rust flags in the ASM cargo build, and we're going to have a look at the assembly. Alrighty, so now that I've compiled that, if I go back to that depths folder, you can see there's a Rust assembly play there as well. And if I do a search for Rust assembly play, you can see there's kind of multiple entries there, but now it sort of brings me back down, and I'm roughly at my kind of main function. So one of the problems with the S files that you've seen there, it's actually pretty hard to read. There's a lot of gubbins within there. So what you really want to be able to do is have a look at something that just makes it a bit easier to read. So I'm going to use a tool called cargo show ASM. So I'll just do cargo install cargo show ASM, and then that'll take a second to get that installed. Once that's installed, what I'm able to then do is run a piece of code that will make it a little bit easier to read. So I can do cargo ASM rust assembly play, And then one of the things I can put in is the name of the function that I want to display. In this case, I know it's called Rust_assembly_play, main. I'll show you in a second how you can find out those answers. So I want the dev build, so I want that to give me a debug file, hence why I'm using --dev. I need to put in my target again, so in this case it's x86 64-apple Darwin. And then the last thing I want to do is say interleave my Rust code with the assembly so I can look at that. So if I run that there for a second, you can now see it's sort of come back, and it's a little bit easier to read now, right? So I've got my my code here. There's my fn main, and then it's showing you some of the assembly code. And then as you are going through each line of code, you can see my let num equals 10, and then the associated assembly that goes with that. So that makes it a little bit sort of easier to read. But don't worry, this is probably still looking quite scary, but we'll break it down a little bit further. If you don't know what the name of your function is, you can just type in cargo ASM and hit return, and then it's going to give you some options. So you can see there's a whole bunch of sort of generated functions that we don't care about, but there we go, Rust assembly play, main. However, even then, it's probably still a little bit complicated, but here's an even simpler way of doing this. So I'm just going to open up Brave, and then I'm going to go to a tool called godbolt.org, and then what I can do here is this is a sort of a compiler which will generate the assembly for loads of different languages. I just need to select a Rust here, and then you can also see that you can pick the various compilers that you want to run. So I'll stick with Rust 163, and then I just need to paste my code in here. So if I take my main RS that I've got here, and then just copy this, and then just copy this into Compiler Explorer. To make the main function work with Compiler Explorer, I just need to set it to being public for a second. Once that's done, it'll work. And one of the nice things about Compiler Explorer is it's actually very nicely generated. So it's quite easy to read and understand the code. So rather than necessarily messing around with cargo ASM, you could just go into this for simple lines of code for you to understand what's going on underneath the hood. And I think it's a little bit simpler, so I would recommend that you use godbolt.org. It's probably the easiest way of doing it. So the first thing that I want you to see at the moment is you can see there's a nice little label there which is example main. So what I've got is my function called main here, and you can kind of see that it's represented here. So there's my function. Now this first line is called sub, and then RSP, usually that is referring to the stack pointer. So if you think about functions for a second, functions are held on a stack. And as I call through my functions and then I call other functions, then essentially I'm sort of working through this stack. Now I'm not going to go through this in too much detail. Stack is very fast kind of memory, but essentially just think of function. And within the stack, and if you don't know what a stack is, it's like a kind of it's like a stack of papers, right? So if I want to add something to the stack, then I push onto the stack. So I might push an item and then push another item, push another item, push an item, and I have a stack of papers. And then when I want to take something off the stack, I just pop it off, pop. So that's really what's going on underneath here. But essentially every function's allocated a stack frame, and therefore every variable that exists is sort of constrained to that. So really what is happening when you see this sub RSP 104, there's a starting point of the stack, and it's saying subtract 104 bytes from that. So basically it's saying allocate me 104 bytes for the example main function, right? That's really what's going on here. So it's a sort of fixed size of a stack frame. So it's just saying everything I need to do is going to happen within this 104 bytes. So the next thing that's happening here is you see this MOV, EAX, and then 10. So essentially, if we come back to here, you see let num1 equals 10. So the next thing that's happening, I want you to see here, is you see this EAX, MOV, so that stands for move or copy. So, and what essentially happens is two arguments. First argument in this case is a register, and the second argument is a value. So really what it's saying is copy the number 10 into a register called EAX. And you can kind of see at the moment there's a sort of one-to-one between variables and registers. It's a little bit more complicated than that because they're going to get reused, but essentially that's what you're seeing in this particular case. So let num1 equals 10. So in this case, it's take the value 10 and stick it into the register EAX. The second thing that you've got here is I've got let num2 equals 20. So in this case, it's saying take number 20 and then stick it into the variable ECX. As it stands, I've got a variable called EAX. So the first move statement, EAX, is now going to have the value 10, and then the second one, ECX, is going to have the value 20. If I come back to my code for a second, the next thing that I'm going to do is I'm going to take variable num1 and variable num2, I'm going to multiply them together, and I'm going to stick the result in a new variable called result1. So let's see what's actually happening underneath the hood here. So you can see there is a nice little assembly operator here, which is imul, and what's that saying is essentially you're going to be doing a signed multiplication of two operands, so that's fine. So, and it's going to take ECX, and it's going to multiply it by EAX. Now the key thing that I want you to understand is EAX is the starting position, ECX, which is 20 at the moment, is going to multiply by whatever is in EAX, which is 10, and then the result is going to be stored in EAX. So what will now happen is EAX will no longer have the value 10, it's going to have the value 200 because it's taken the 10 and the 20, multiplied them together, and then it's stored it in EAX. Now, the reason it can do that is there is nothing else accessing the register EAX. Now you might be thinking to yourself, hang on a second, there's a calculation here which is num1 multiplied by num2. So you might be thinking to yourself, hang on, surely it's got to access EAX again because I'm going to take that value num1. We'll come on to that in a second, but the answer is essentially no. It doesn't need that value because the compiler is going to do some optimizations, which I'm going to show you in a second. So the next thing that happens is it's going to take the value EAX. So EAX at this point is going to have the value 200, and then what it's going to do is going to do a move, which is a copy, and it's going to take that EAX value of 200 and it's going to put it in essentially a memory location in the stack frame. So if we look at this, you can see RSP plus 32. So there's pointer to this is our stack pointer, remember RSP over here. So if we just add 32 bytes onto there, so 32 bytes onto where the stack pointer starts, then essentially from there, the value 200 is going to be stored there. Now that is a good thing to be aware of because essentially in advance, fixed calculation sizes of storage of local variables is going to be calculated and be able to store within that stack space. So it's all calculated up front, right? So that calculation, result 1, which is num1 multiplied by num2, because we know that's a 32-bit integer, that can be stored in there and there's a fixed allocation size that's going to occur. So there we go. So if we come back to the slide for a second, what you are going to see here in my stack, 32 bytes from the stack pointer, you're going to see the value 200 sitting at the top there. So it's just sort of popped on there. Now the next thing that's happened is you've got this seto thing. So what is seto? So and it's doing it on the register A1. So what seto is doing is actually testing for an overflow. So if I have two integers multiplying together or whatever, and then it goes bigger than the greatest size of the integer, so let's say in this case it's an I32, so if I have a very large number, then essentially you get into this overflow scenario. So what Rust is doing here is putting a little bit of assembly code in here that says go check to see if an overflow just occurred. And if an overflow did occur, then stick the result of the overflow in A1. So once that's done, it's going to do a test for the overflow, and then if an overflow does happen, it's going to jump down to label _2, so LBB3_2, and then essentially what it's going to do is panic, and you're going to get an exception of some sort. If everything is fine, if there's no overflow, it's going to continue on here. So the next thing that's going to happen is we're going to take the value, whatever is in D word pointer, 32 bytes from the start of the stack pointer, and it's going to load that in to register EAX. Now, if you remember, EAX has got the value 200 stored in there, right? So it's got the value 200 over here. So what's actually happening in this case? Well, actually, this is kind of smart enough to realize that num1 multiplied by num2 is a calculation that's already been done, and it was stored in result 1. So the compiler's kind of worked that out, and that's something to be aware of. Is the compiler can do some basic calculations, so things like additions, etc., or have a look at where there's some duplication, and then be able to do some reuse. So now as it stands, in EAX, we're going to have the value 200. Now, the next thing that it's going to do is with the register ECX, we're going to put the value 2 in there. Again, if we come back to the slides for a second, what you can see here is EAX has got the value 200 and ECX has got the value 2. So what's going to happen now is we're going to do another imul, and if we remember that from before, then it's going to take whatever is in the second operand, which in this case is 2, it's going to multiply it by the first argument, which is EAX, great? So it's going to be 2 multiplied by 200, and that's going to be equal to 400, and that's going to be stored in EAX. So EAX is now going to be have the value 400, and then what's going to happen is it's going to store the value 400 in RSP plus 28. So I want you to come back to that stack for a second, right? So result 1 has got the value 200 in there, but then if we go slightly higher, so just one up on the stack there, what you're going to see is the value 400 is there, and you can see that it's 4 bytes apart from the 200. And that's because of the sizes of the integer. These are fixed sizes. So if I change that from being an I32, for example, and I put some other value in there, maybe it was a float or something, or it was Boolean, then that's going to have a different sizing. So this is all of the sizing. This is where it's using your types and the size of your variables to calculate the amount of memory that it needs within the stack and how it is able to be super fast. So anyway, we've now got 400 stored in that location. And again, if I come back to my keynote, you can kind of see that here. Now I've got 200 at RSP plus 32, and then I've got 400 at RSP 28. So it's using that allocation of memory on the stack to go along. So the next thing that is then happening is it's doing that kind of seto piece again, and then it's also doing another test. So it's basically checking for an overflow once again. And if an overflow happens, it's going to jump down into label 4, which is going to panic again. But if underneath the hood, everything is fine, it's going to jump to label 3, right? So, by the way, just so everybody, let's be utterly clear here, these label jumps, these are go-to statements, right? So, for everybody that goes, oh yeah, go-tos are terrible, and they are in the higher level programming languages, but actually underneath the hood, that's how assembly works. So, if we look at this line of code here for a second, what we're going to do here is we're going to take result 1, which we know is 200, and we're going to add it to result 2, which we know is going to be 400, and then we're going to store it in result 3, which will give us 600. So, let's look at the underlying code there for a second. So, the first thing I can see is I've got a move statement, which we know is a copy, and it's going to take the value from dword pointer RSP plus 28. So, it's going to go to the memory location in the stack of plus 28 from the stack pointer. So, we know that was 400. In fact, we can come back to our slides there. There's RSP 400, RSP plus 28, which has got the value 400, plus 32 has got 200. So what we're going to do is we're going to take that value and we're going to put that in EAX. So EAX, the register, is now going to have 400. The next thing that's going to happen is we're going to take the value 200 and we're going to add this to EAX. Why is it not just actually pulling in from dword RSP plus 32? And that's because the compiler is smart enough as it's going along, right? It knows that the value is 200 in this particular case, so it's done a little bit of compiler optimization and it's just shoved 200 in there and then it's done the addition. So this is one of the things to kind of be aware of, right? Especially for addition functions, if it can do some simple calculations and a compiler can work this out in advance, then it will do that. Now remember, these values here are all immutable in Rust, so there's no chance that they're going to get changed or anything underneath the hood, and the compiler's done all the calculations. So it's pretty good, and it's just doing that. So EAX, if you think about it, what's going to happen here, and the add command is very similar to the mul, so what it's going to do is it's going to take the value 200 and then it's going to add it to whatever is in EAX. So remember, this is an add, not a move. So if it was a move, EAX would have 200, but because EAX has got 400 in there already, it's going to take 200, add it onto the 400, and then put the result in EAX, which is going to be 600. And then, of course, the next command here that you're going to see there is it's going to take that 600, which is in EAX, and then it's going to put it to RSP plus 24, so the stack pointer plus 24 bytes, because essentially we're dealing with 4 bytes here. So that is now copied in here, and the value 600 will be at RSP plus 24. So come back to the code for a second. What you're now going to see is EAX obviously has the value 600, and now 600 is stored at RSP plus 32. So I've got 200, I've got 400, and now I've got 600 at RSP plus 24. So now that it's done that calculation, it's obviously going to do some further tests again for overflows, etc. And then it's either going to jump to number 6 if there's an overflow, so label 6, and it'll just panic. And if it hasn't panicked, then what it's going to do is get down here, and then essentially it's going to set itself up to do the final print line. The value of the result is blah blah. So I'm not going to run through this piece here because it's going to eventually land at label 7. It's going to run through all of this, and then you can see sort of standard value studio print macro, and that's then going to call the standard function, which is going to print out the value of the result is blah blah. So that's kind of how that works.
And I'm going to try and do something geared towards what I like to call maybe advanced beginners or beginner intermediates, depending on how you think about it. So this stream is really geared towards people that have done a little bit of Rust before. They've probably read through the book. They've probably done a toy project or something. The concepts are familiar, if maybe not quite 100% grasped. You've at least heard of things like the borrow checker and lifetimes and things like that. And today what we're going to be trying to do is go through a project where we kind of put some of those concepts together and really try and see how all these things work together. Real quick, as I switch over to the browser scene here, this kind of came from the results of the 2019 Rust survey, which at the end, there's a conclusion at the very end, which basically says that we need more learning material for intermediate users. And it's kind of hard to know what an intermediate user is. Some people who are fairly confident in Rust claim that they're beginners, some people who, or vice versa. So I'm not exactly sure what an intermediate user is, but what I'm aiming for today is kind of that advanced beginner. You've read through the book, you've heard of the concepts, and today we're going to put it all together. I want to give a quick shout out here to John, who's also been doing some streaming as well. I mean, if you've not checked out John's stream before, or his YouTube channel, please do. There's a ton of awesome stuff there. He's really super great. And he did on Wednesday a stream that kind of aimed at going specifically over lifetime annotations, which today we'll touch on briefly. But the truth of the matter is that lifetime annotations aren't needed a ton in Rust, and so this is a really specialized topic. I haven't watched his stream on this yet. I kind of wanted to go into this without being biased towards the topics that he touched, but knowing his past work, for sure, it was a great stream, and seems like a lot of people enjoyed it from what I saw online. But today we're going to be doing something a little bit different. The most important part for those that are watching live right now is to ask questions. We're going to try and go through this, and in a way, I'm going to try to make a bunch of mistakes or try to go down paths that won't really work out fully, even though I've done this exercise before and I know how this code should work. So, depending on how much I remember of when I've done this kind of coding before, I may be biased towards not making mistakes, but please make sure that I do. So this is the first stream, perhaps in history, where people where I actually want to really make as many mistakes as possible, and I'm relying on the chat to make sure that happens. So what are we going to be doing today? Well, what we'll be doing is working on a small little library for doing a thread pool. And this is not going to be a library that people will actually use at the end of the day. There's a ton of things that it won't do. It's a very naive implementation. But the nice thing about thread pool is that we really kind of have to dive into how lifetimes work, or how the borrow checker works, when things are dropped, how long things live for, things like that. As I said before, we won't really be annotating that a ton, but we still have to have an understanding of that because the Rust compiler will complain when we do something that is not fully correct. At the end of the day, what hopefully we should get out of it is a thread pool library that allows us to execute work on a pool of threads, where we kind of robin around the threads, and we'll write some tests for it, and even the tests will be illustrative of how we should think about borrow checker and things like that. So hopefully everybody's ready to go. Again, chat, let me know if you have any questions. So what I'm going to do, first of all, is create a new project. So we're going to do cargo new lib, and the hardest part of the day, of course, is always coming up with a name for your crate. I'm going to call it thread pool because I'm feeling very creative today. So let's go into thread pool, and then I'm going to open it up in VS Code. Oops, I should probably switch over to this so you can see what I'm doing. Just for your knowledge, this is what I did before. Cargo new lib thread pool, went into it, and then opened up VS Code. So pretty straightforward. And of course, if you've done some Rust before, you know that this is what you kind of get by default from a library. So great. So I think the first thing that we're going to want to do is to kind of spec out the shape of what we want to do, maybe come up with a simple public API that we want to expose, and then start filling in the details from there. So probably the first thing that we want is a public struct called thread pool, I would guess, and we'll just put nothing in it because we don't know what we need quite yet. And then we'll have a thread pool where maybe we do a new function because that seems like it will be good. And let's see, we'll just do it like this. And of course, we want that to be pub. And then what I imagine we will have is kind of an execute function of some sort, like this. And it's going to take something, but we'll talk about that in just 1 second, what that might be. And for now, it won't return anything. Probably today won't return anything. So this is what our public API is going to look like. Great. So we have our thread pool, we know how to construct it, we know how to call execute on it. Of course, that's not going to do anything right now, but just to get our tests kind of bootstrapped, let's go ahead and do pool equals thread pool new. And in order for this to work, we need to bring our thread pool into scope like this. All right, what is it complaining about here? Failed to resolve thread pool. No, it's because it's capital P. Great. So now we have our thread pool, and we would want to call execute on it. So pool dot execute like this. And it's going to complain because we forgot to do a ampersand self up here. And the reason I'm doing ampersand self here is because we presumably want to be able to call pool.execute kind of over and over again like this. And so if we were to take it like this would mean here that we are taking ownership of self, moving it into the execute function, and that means that pool here is no longer valid, which is the error that we get. We're using pool after it's been moved into the execute. This is a good time to stop and say, if what I just said makes absolutely no sense to you, then the stream might be a little bit more advanced than what you're ready for. So go back to the book and read that and then come watch this later on. Or stick around and just enjoy as I type things. But if the words that I said have some meaning to you, even if you're not 1000% comfortable with the ideas that they represent, then this is perfect for you. And this stream is going to hopefully kind of solidify those ideas for you. Okay. So we have execute here, and now the next thing that I want to do is I know that for our execute, the kind of API that I want is to be able to pass in a closure like this, and then do some work. So like, let's say print line, hello from thread, like that, and we should be able to kind of do this the same here. And we should be able to get the thread ID so we can later on look at kind of make sure that we're running these two things on different threads here and stuff, but we'll get to that later on. Okay, so the reason it's complaining here is because execute needs to actually take that closure. So if you've not done, if you've probably used closures before, if you've done any kind of Rust, but you may not have had to make a function generic on closures before. And so what we're going to do is do a generic parameter like this, and closures are things that implement these kind of special closure traits. And so we can't just take a concrete type that is a closure, we have to take a generic type that implements one of these closure traits. And the most common one is this fn right here. And so this would be work or something like that, and it's going to be like that. Okay, so what we said here is we have some generic type t, it implements this fn closure trait, which is a special trait that basically says this is a regular closure, and we'll talk about the other variants of closure traits, fn mut and fn once, a little bit later on. And we know from the signature that closure takes no arguments, returns nothing from it, and we're going to pass that in as work here. And what that means is that every time we call execute, we'll be actually calling execute on it. We'll be calling a different execute function that is specialized for the work that is done, inside of these closures. Because these closures, I'm not exactly sure if these particular closures, because they do the exact same thing, are different from each other. But if you have different closures that do different things, then they will be different concrete types. So is everybody good with that? Any questions from chat or anything like that? Great. Okay, so I think now that we've got kind of the shape of our library up and running, then we can start actually doing the implementation work. And so I think the first thing that any good thread pool needs is threads, probably. And so what we're going to do is spawn off a bunch of threads that will kind of exist in the background. And this is not going to be a thread pool that supports kind of lazy instantiations of threads. We're just going to, when you create the thread pool, you just create a bunch of threads. Maybe not the most efficient way to do it, but it's what we're going to do for now. And so I'm thinking about this, and maybe for our thread pool new, we want to take like a number of threads that we want to actually create here. So we can do something like num threads. And I'll just do a U8 here because it feels like, if you want to create more than 256 threads, that's, I don't know, that's quite a lot. So maybe you can make the argument for U16, but like a U64, we don't want to be creating, I don't know, millions or billions or trillions of threads. And so what we're going to do here is just do a simple for loop. So boom, for blank and 0 to num threads. We're going to call standard thread spawn like that. And we have to pass in a closure. And so here we've actually spawned our thread. And of course, we spawn returns back the thread handle. This handle allows us to say, okay, this thread we want to block and wait for it to be done. So we can just get that handle back so that it stops complaining about it. And here it's saying, hey, I expected to find a semicolon. Where's my semicolon at? And so we go ahead and put that down there. Okay, so now we're going to have a bunch of threads, which is really great. And I don't know if we'll need it, but we can go ahead and just hold on to these thread handles. So let's do handles, and then we'll do standard thread. Isn't thread handle or join handle? Sorry. Join handle, and it returns, that join handle returns nothing to us, like that, and close off right back here, and then we can come down here and say handles like that. And so we need to, let's go ahead and turn this into a map real quick, and we will go ahead and do like this. So we're going to iterate over the range, map, and ignore what we're getting there, and we're going to then collect into a vector, like handles, like this. Do we not need either here? Yeah, we didn't either. Okay, cool. So now we are mapping over our range, and for everything, we're spawning a thread and then collecting it into our vector of join handles and holding onto them. We have to get rid of this. Awesome. And then down in our test is complaining because now we don't say the number of threads that we want, so let's just do 10 threads for now, and that should be good. Let's see. We have some questions here. Are these Rust threads directly mapped to OS threads, or is it something similar to lightweight Go routine? So threads in Rust are OS threads. Way back in the day, before 1.0, Rust did have green threads, and they got rid of it. The reason for it is that Rust is meant to be a systems level language. It's meant to be, it's meant to have zero cost abstractions, and if you have green threads, you have to have some runtime that keeps track of those green threads. And so this kind of went against the Rust philosophy that if the Rust philosophy, I guess one way you can sum it up is any kind of abstraction, if it costs something, it should only cost something to you if you actively use it. And so if you don't use that abstraction, then it shouldn't have any cost to you at all. But green threads do have a cost whether you use them or not, because you need to start up a runtime. And so everybody would have a green thread runtime, no matter if they use them or not. And so they were removed. And Tokyo or async standard or any of those runtimes now kind of have that that idea built into them. And so when you use Tokyo, for instance, you go ahead and start up a Tokyo runtime or async standard. You start up an async standard runtime, and then it gives you the ability to spawn tasks, which in effect is green threads. And let's see, difference between Tokyo threads and standard threads. Hopefully that explained it. And yeah, Tokyo thread, Tokyo and async standard, I think both use the term task instead of thread to kind of avoid this confusion. But yeah, you can think of them like green threads, exactly. All right, awesome. Okay, so we have everything running. We have threads that we're going to spawn to, and now what we need to do is figure out that how we're going to actually kick off the work. So every time we spawn a thread, what we want to do is have some way basically of, one second there. So we need to have some way of doing some work, checking that if there is some work to do, doing that work, and then looping back and figuring out if there's more work to do. And so I think a great way to do that would be inside of the spawn to literally just loop forever. And then like we need to check for work. And if there, once work, do work, and then loop back kind of thing. And so the question is, how can we check for work? And a great thing that comes with the standard library, come back here, is channels, which are again going to be familiar for any Go programmers in here. Why is this not working? Here we go. So here we have inside of standard sync MPSC, which stands for multi-producer single consumer FIFO-Q, which allows us basically to send messages across threads, which is exactly what we want to do. And if you're familiar with Go, then Go has concepts just like this. I think what we want to do is have a sender and receiver, and what the receiver will do is receive, will kind of inside of the thread, listen for work, do check if there's work, block if there's not work, and then once there's work, it will get it and do the work and then move back around. And so what we want to do here is we're going to have a sender and a receiver. You'll also oftentimes see this as TX and RX, like a transmission and a receiver. But I like that for today. I'm just going to spell it all out. And then up here, we'll go ahead and we'll do includes up here. So use standard sync MPSC. And we need right now a channel like this. So we're going to be doing channel. But channel is generic on some type, so it needs to know what type it's going to be sending back and forth across these threads. And so what we can do for now is just say that it's going to be unit. It's going to be nothing. We won't send anything. We're just going to basically, notify. This is another way to implement some kind of notification API that just says, hey, something happened. What we do now is our receiver. We're going to move that receiver into this thread here, and we're going to check for work. So we can do receiver dot receive right here. And receive returns a result here. So the reason it returns a result is because if the sender is no longer there and the channel is kind of broken, then receive will stop blocking and return an error letting you know that the channel was kind of was broken up. Great. So we need to, I think for now we'll just go ahead and do unwrap like this and just crash the program if the sender and receiver is kind of break up from each other. This is not what we should do, but we'll fix that a little bit later on. And then, so we've checked for work, and receive, again, blocks on the current thread, which is this thread that we spawned, and when it gets a message, it then returns. And so here we'll have our message, and that basically signifies the work that needs to be done. And so the question now is, what work do we need to do? And what would be really great is if we could just get this this function down here, receive that, and then go ahead and call that work. But of course, like if we come up here, we're sending right now a unit struct or a unit tuple here that doesn't really tell us anything. We want to be able to do something like like this, right? Like send me a function and then I'll call it. But of course, if we read this, it's like the size or value of type standard ops fn cannot be known. What it's saying is that channel basically requires a type, not a trait. And fn again is a trait, so it really needs a concrete type. The reason for that is it needs to know the size of the thing that it's receiving for. And a trait has no size. A trait is just a compile time concept, whereas structs actually have a layout memory. They have a defined size, so the compiler knows, okay, I need to reserve this much space on the stack and stuff like that. So we can't do that. Now. I think the best thing to do when you have a trait of some sort, and you just want to be able to work on things that implement that trait, but you don't care or even know what concrete type they are. They might be different concrete types, which is going to be the case with our closures here. These closures are going to be different types because every time a closure is created that captures its environment differently or whatever, it has a different concrete type, some magical compiler type or whatever. But when we don't care about that or don't know about it or can't know about it, the best thing to do is to take that trait and box it and put it on the heap so that we can call the trait methods in a way that's called dynamic dispatch. We basically say, put it on the heap, I don't know what it is, but I know that it has these functions, and let me call these functions through a virtual table, a V table. And so what we want to do here is do this. And we'll get a warning here where it says this is a trait object. This is an object where we call its methods through a V table, and it's not yet quite a hard error, but in the future it will be required to explicitly notate that in the syntax and say this thing is dynamic. It's a trait object. It's dynamically dispatched. There is no static dispatch with this dy in. So again, the object that we're sending over our channel is a box. It's a heap allocated pointer, and it points to a function, sorry, a closure of some sort, and we can call that closure through that pointer basically. So this will work. So now what we're getting back here is our work that we want to do, and again, this is our boxed dynamic function here, dynamic closure, and of course we just want to call it work like that. So this is great. I'm going to stop real quick. I think there was a question, and wait if anybody has any other questions about why we needed the box, about what dynamic dispatch is, anything like that. More than happy to answer those. Let's see. 0 num threads yields a slice is the question. No, it does not yield a slice. This is a, let's see if I can get, oh, you can actually see it right here. It's a range. It's a range of U8s that we have there. And ranges are simply, a start and end, two numbers together. All right. Okay, so another question we got was, what is boxed dynamic dispatch? Okay, so let's explain that one more time. When you call a function in Rust, like deadline, foo, and we have another one. If I call foo here, foo is really a function inside of my binary, and when we call foo, it's simply what will happen is we jump to this function and we call it, and of course there are, really at the end of the day, there's a whole bunch of things that needs to happen, like we need to put the arguments somewhere, like in registers on stack, blah, blah, blah. We don't need to worry about that, but really at the end of the day, this is just a straight function call, nothing fancy going on. When we define foo generically though, like this, where we're going to say, we have some type t, like this, and I think we need, where is debug? Debug is in standard, real quick, format. Standard format debug here. So we're taking some type t. It's a concrete type. When we call foo with something, we'll call it with the number 1 as u8. What we're saying here is we will create a foo function that works specifically for u8s. And if we call it again right here, where the item is a string like this, then there will be another function in our binary that is specifically meant for strings. So now in our binary that we've created, there will be two foo functions, one that's specialized on u8s and one that's specialized on strings. And if we call foo with different items, it will keep on creating more and more special foo functions. Of course, if we call foo here with 2 u8, then these two foos are the same thing, and this foo is another foo that's specialized just for strings. Okay, this is the technical term for this is monomorphization. So you're basically creating a function for every concrete type of thing that implements the trait that you've set for. And what's awesome about this is it's very fast. It's simply a function call, and you have a specialized function for every single type that you created. The thing that's not so great about it is that if you use this function with a ton of different types, then you'll have copies of your function for all these different types, and that might blow up your binary size. So, but you gain in speed, you'll lose in binary size. Now let's say we don't want to do that. What we want to do is say, give me one foo function, and I don't care what the concrete type is. I don't know what it is. I don't want to know. All I know is that it's something that implements the debug trait. What that means is we, instead of calling some type t that happens to implement debug like this, we're going to say we are taking literally the debug trait like this. This won't work. And the reason that it won't work is the debug trait is just some compile time fantasy. It doesn't really exist in our program. It's simply a trait. It's a collection of methods that something might implement. But when you call a function, you need to know like a specific type. It has to have a well-known size so that Rust can, for instance, create enough space on the stack and stuff like that. And so one thing that we can do is take this by reference instead. And the reason that this works is how big is a reference to something? Well, it's a pointer basically. Now that's not quite the real answer, but Rust knows now how much space the item argument takes up. It knows exactly how much space that is. It is simply a reference to a trait. And of course, we're getting the same complaint here that we got above. That'll show you that this used to work, but we need to be explicit now that this is just a trait. So we do ampersand done now. And so item here now is some pointer to debug, and that means it will go through a v table. To get there. That's how you call methods on trait objects. You go through a v table. So while you maybe didn't understand everything there, hopefully you understand now when you have generic argument, you literally create copies of that function for every single type. It'll specialize, the compiler will specialize for each type. And if you have done here, then what that means is that you're taking a pointer to some object that's out there, and it will go through a virtual call table, a v table, to call functions on that. And what this means is you save, it's a little bit slower because you have to go through a v table to call it. So there's like a little bit more indirection, which means it's a little slower. But there's only one foo function now, only one. And it's this one right here. Hopefully that works. Today's not exactly about dynamic dispatch, so I think that's the last we'll probably talk about that. But
think I'm gonna start the stuff right away because otherwise I'm not gonna start and it's already late. So I'm gonna spend 1 more hour here. And I think I'll continue to train off stream and probably tomorrow as well. I'm definitely gonna do it every day. The Vim
And welcome to
stuff.
Coding and Crypto. And welcome to my Rust beginner tutorial. So I'm assuming if you found your way over to this video, you've probably already heard about Rust. You've probably already seen some of the benefits of using Rust. If you haven't, I'm not going to dive into all those things right now. So I encourage you to go take a look on the web. There's some really awesome articles touting all the features of Rust, so definitely go take a look. And we'll gloss over all those features as we learn all the functionality of the language. And so you'll see some of those benefits start to come to the surface as we go. But without further ado, we're going to get right into coding. So the first thing I'm going to recommend you do is whatever IDE you decide to use, this is going to be VS Code, is just go in and get a Rust plugin. This will help with like code completion and with sort of like being able to look up different functions and stuff on the fly. And so that'll be very helpful. The next step is we're going to install Rust. So the easiest way to do this is just search install cargo. And cargo is Rust's package manager. So if you guys have ever used like Java, you've probably used Maven or Gradle to support your packages and your builds. That's what cargo is. It's a package manager, which is going to help you keep track of all the dependencies, like different Rust programs or modules.
Yeah, so like I said many times, I'm gonna follow the tutorial, copy the stuff that he's doing, and then at the end of these tutorials, I'm gonna go on my own and see how I can change the code that I have to do the things that I want to do.
That your app is going to need. So the easiest way is just click this first link. It's going to be the rustlang.org. And it's actually Rust's official docs, so feel free to take a look at everything that's in here. Setup instructions are for Linux and Macs, and then down here, you've got Windows machines down here with this rustup init.exe. So go ahead and download that. Now, I've already downloaded a few times, and I have this installed already, so mine's going to be pretty quick, but you should have the same process. Yeah, Defender's not a fan, by the way. But run it. I'm going to select number 1 with the default installation. And when it's finished, you're going to see this. Rust is now installed. Great. Awesome. So now we can get out of here by pressing enter. Close this out. And when you open up a new project, just double check that cargo's installed by trying to type cargo. And you can see if the help menu comes back, you got it. So now we've got everything we need to get started programming. So we're going to build a little like example application where we're going to take some user input and we're going to print out some strings and we're going to pretend like we're sending and receiving Bitcoin. It's going to be super fun and we'll learn a lot about Rust in the process. So the first thing you're going to want to do is type cargo new and we're going to call it send Bitcoin. So that'll create a new binary application called send Bitcoin. And you can see it up here and it generates some files for us. So the first one is going to be cargo toml. Now, unfortunately, I haven't found a good plugin yet to make this look nice, so it's all the same color, but you can see that under the package key, we've got information about our application. So the name, the version, the edition, and there's other keys that you can use to describe your application and put labels on it. And right here, Rust provides a link to that. So you can go and check out how cargo toml can kind of be expanded. But right here under the dependency section is what's going to be crucial. So this is where you're going to declare other Rust modules that your program is going to need. So anything that doesn't come default automatically with the standard package of Rust, you're going to have to call in here. So to show you what that looks like, we're going to need this particular module called ran to generate a random number in our example app. So we'll save that. And we can close that out because that's really all you need to focus on right now for cargo toml. And now in main.rs being a Rust file, you can see we've got this main method. Now, the main method is the function that Rust is going to look for when you go to run the application. Okay, so everything gets run out of main. It's your driver function. In fact, in IntelliJ, if you open this up, a little play button will pop up right here, so it'll let you know that. But if you've ever written in Java before, public static void main, right, that's the same concept. And even Python has a main method that you can drive your script with. So pretty neat. Now, this is going to print hello world, obviously. But how do we run this thing? We'll just do cargo run. But before you do that, don't make a mistake. Make sure you CD into the directory that you're working in. So we're going to slide into send Bitcoin, and we're going to do cargo run. And you can see that what's actually happening, so there's our hello world, right? We got the output. But what's actually happening here is cargo run is going to build your app and then run it. So that's the same thing as doing cargo build and then running it. But you can see right here, Rand was installed, and it was built and pulled into the application while we were building our app. So you can see cargo makes that program available to us to use. Awesome. So let's start writing a little example app, get our feet wet with some Rust, and then in future videos, we'll break things down and talk about it at like a granular level. So the first thing we're going to want to do is we're going to want to set up our like initial core function of what we're going to do. So this is going to be kind of like a command line app, I guess. And I like to keep things organized. So this is how you write functions in Rust, if you couldn't tell from the main one. And if we just put all of our stuff in console and we just tell main to run console, that's how you call another function. So in console, we're going to use print line, and print line's got that exclamation point in there. And we're going to say, let's have fun with Bitcoin. And I like to put these \n to try to create new, or / whatever that is, to try to create new lines and kind of space out some of these outputs. So cool. We know that that's going to just print that out in raw form. What about if we wanted to actually, what do we want to actually do? Well, let's start by asking if they want to send or receive Bitcoin. So do you want to send S or receive R Bitcoin? And I always forget about this, but do not forget the semicolon here. Usually the IDE will catch you, but Rust is very particular about semicolons. In fact, in a future video, we're going to cover the omission of a semicolon. If you purposely leave it out at the end of a function, that's actually how you do a return. Like you don't have to type the keyword return if you just have no semicolon. So kind of neat. We'll cover that later. But remember to include that most of the time, all the time right now until we cover that. So to start out, we want to take the user's input, whether it's an S or an R, and we want them to dictate what our app's going to do, right? So let's say let command equals string new. So this is how you create a new string. We've got the string struct, and then we're using a method from this struct called new to initialize a new string object. And we'll cover structs later on. So what we're going to want to do now is overwrite this value with the user's input, and they're going to ideally put in an S or an R. Now, in order to overwrite this,
I don't think I'm gonna copy everything in the beginning because it's not related to the project. I'm only gonna copy when he starts talking about the actual project. I think it's gonna be on the later tutorials here. Yeah, it starts on this one, I think.
Now, this value, by default, when you use the let keyword, which is how you define variables, and nothing else in here, by default, this is going to be immutable. So you can't change it. In fact, if I try to go down here and say command equals, let's just do like string from, and this is how you create a string from a small string slice or something like that. Let's just say like Homer. Rust is immediately going to say, hey, you can't do that. Well, actually, it's telling us that it's never being used, but the real error there is that you can't just overwrite this because, see right here, you can't assign twice to an immutable variable. Now, all we have to do to make it mutable is this. Just add that mute command or keyword. You have to explicitly tell Rust that a variable is allowed to be changed. This is part of like the benefits of Rust is you have to be very explicit a lot of times, but it saves you a lot of trouble in the future. It can prevent a lot of bugs by being very explicit about your instructions. So anyway, now that this is mutable, we're going to overwrite it with the user's input. So this is the function to use to do that. It's this IO object here. We're going to use stdin and read line. And we're going to type that and sign, mute, and command. Now, we're going to come back to this in 1 second, don't worry. So the first error we're seeing with Rust is it's saying this is undeclared crate or module. So in other words, it doesn't really know what this is. Luckily,
Yeah, actually, just gonna copy once he starts the tutorials. I'm gonna watch this fast, and then when it gets to these points, I'm gonna
as part of Rust's internal library that
copy
comes
this
involved with
stuff.
every program, you get the std library, and you can use stdio. But how do we import this? Well, in a lot of languages, the keyword is import, but in Rust, it's just going to be use. And you can see that error went away right away. So we're going to use this module, this package, and we're going to read user input with it. Now back to this. So what is this thing here? I mean, you can see that stdin is going to create an input, and then we're going to read the line from the user. Makes sense. But what is that? So basically what we're doing here, and this is a little bit more complicated. We're going to cover it in a couple videos from now, but we're making a reference here. Now, in this particular case, we are referencing the mutability of this variable command. So essentially, we're checking with Rust right now and saying, like, hey, remember earlier when we said that command was going to be mutable? Well, here we are making that change with this function. And Rust is saying, okay, cool, no worries. So that's all that is there. In a video or so from now, we're going to cover references and borrowing. It's a really important topic, and this will become a lot more clear. But regardless, we're going to just mutate command with the user's input. Sweet. So we said that we want them to enter an S or an R, right? So let's check to make sure that they've actually entered one of those values and handle it if they don't. So here's the first look at conditional in Rust. And we're going to say if command, we're going to trim it to get rid of any like new lines or anything that get generated from the user input, equals .eq s. If it does, we're going to do this function send Bitcoin, right? If it does not, if instead command.trim is equal to eq r, then we're going to do receive Bitcoin. I really think I'm going to spell that wrong a lot. Else, if it's neither s or r, then we're going to do is just this exit console function. So as you can see, we're taking the input from the user and then we're comparing it to either our s or r options. And if it's neither, we're going to do this little exit console. So these are all going to be functions, obviously. And let's go find those. So for starters, we'll do send Bitcoin. And we're going to come back to this one, but I guess we'll just put something up there right now. We're going to do also receive Bitcoin. Put something in there as a placeholder. And then lastly, we're going to do this exit console function here. And this is going to be pretty straightforward. All we're going to do is just print out invalid option. Must be r, s, or r. And we're going to put those in some parentheses there. All right, cool. So exit console, we just wrote that. Receive Bitcoin. So how do we want this to work? Get this out of the way for a sec. Well, if we want to receive Bitcoin, we pulled that random number generator in here so we'd be able to use it. So let's make use of that and let's just write a function that's going to just send us a random number of Bitcoin. I think that'd be pretty nice, right? So anyway, here's what we're going to do. We're going to do a print line. Then we're going to say we're going to receive some Bitcoin. Awesome. Line separators in there. And now we're going to do let amount equal. And here's where we're going to use that random module there. So what we want to do is actually add it to our use statements. We're going to use rand and we're going to use the RNG attribute. So just like that. And now that that's being pulled in, we're going to say let amount equal rand thread RNG dot gen range. And that range is going to be from 1 to 10. Nice. Okay, so that's going to give us a random number from 1 to 10. Now what we're going to do is just print out this statement that says you just received. And here's how you pipe a value into a string when you're printing. You just do these curly brackets. We're going to finish our string, Bitcoin, and then a comma, amount. Nice. Beautiful. Super cool. And then our last function up here is going to be send Bitcoin, but we're going to come back to that in a sec. So for now, I'm just going to put in like a bogus print line, like hello, you know, something like that. And we're going to take a look at what happens with this function that we just wrote here, this receive Bitcoin one. So let's go down and run cargo run again. I'll open this up. And if you take a look down below once this finishes, there's our question. Do you want to send or receive Bitcoin? Let's go ahead, since we didn't do send, let's try to do one that's not in there. Let's do a G. Invalid option. Must be S or R. Sweet. Okay, so let's try again. Let's receive it. You just receive 7 Bitcoin. Woohoo! Wow, 7 Bitcoin. Holy moly. Let's do it again. 7 more. 9 Bitcoin. 4 Bitcoin. So our random number generator is working just fine. That's good. Good to see. Now let's go back up and let's write this send Bitcoin. So again, just like this, we're going to add this print statement here as a header. Instead, we're going to send some Bitcoin. Sweet. Now, let's just have a little fun here and let's come up with like a list of clients. And we'll send Bitcoin to one of the clients. And we're going to make sure that the user only picks someone that's in our client list. So we're going to work with conditionals again, and we're going to get a taste of a collection called a vector. So let's let clients equal vec macro, which is going to turn these entries into a vector. Now, a vector is very, very similar to a list. And for the example today, you can literally think of it as a list for right now. We will cover vectors in more detail later. But for right now, just picture this client's object as a list of strings that represent our clients. And as you can see, there's some characters. Awesome. So now we're going to print out the question. Who do you want to send Bitcoin to? Get a new line going there. And we're going to just print out each of our clients. So we're going to say for client and clients. And we're going to print. We're not going to print line. We're just going to do regular print because we don't need to necessarily skip a line between each of them. And client. And then we'll just print a new line real quick just to have things nice and organized. Now, you can see that and sign has popped up again. So what are we doing with it this time? Earlier we were referencing the mutability of a function as a variable, as we changed it. But here, we're using it to reference a vector. Now, we're going to dive into this concept in the future in a couple of videos from now. But what this is doing right now is it's referencing the value. So rather than pull in this particular value and all the details about it, like its position in this vector, what vector it lives in, this and that, instead, all we care about is this value because we're just doing something like a print, or like sometimes you might want to create new variables based on that value. And we'll get into all the logistics of that. But this is what's called borrowing. We're just borrowing that value so we can run this loop and print all the values out. But we don't need the whole vector itself. We just need the values of each of these things. So like I said, we'll get into that more in the future. But all right, so now that we're just printing out our clients list and the user's going to be able to see who's available to send Bitcoin to, we're going to take their input just like we did down here. So you can literally copy paste this. I'm just going to put this together so it's a little more concise. And it's going to be the exact same function, right? But instead of command, we're going to just change it to recipient. Okay, so it looks exactly the same, right? We're doing IO, SCDN, reline. We're making it mutable. We're using that reference to the mutability to overwrite it. Beautiful. But now we said that we want to be able to check if the user's input matches who's in our clients list. We can't just send Bitcoin to whoever we want in this example. So we're going to write that conditional check here. And we're going to say if clients.contains, and then we're going to say reference that recipient value trimmed. So we're comparing it. We don't necessarily need to pull in that whole recipient string, right? We just need the value. Again, we really only need the value of the string. We don't need the object itself. So if that's what we're going to compare, then let's say, okay, if this becomes true and that entry is inside our clients, we're going to continue with the application. So we're going to do like a print line. We're going to say how many Bitcoin do you want to send? And then we're going to take the user's input again. Whoops, we're going to take the user's input yet again in the same fashion. And this time we're going to call it amount. Right? So now we're taking the input as the recipient. If they match someone in our clients list, we're going to take the amount from the user, and then we're going to send some Bitcoin. So our final print statement is going to look like this. We're going to skip a line and say you sent blah Bitcoin to blah. And now we can declare that we want you sent amount Bitcoin to recipient. Sweet. So now this is great. We're double checking that this matches who's in our clients list, but what if it doesn't? Well, it's pretty easy. It's just an else statement. And if it doesn't, we're going to print blank is not in your contacts. And then we're going to go down and type recipient trim again. So it's a nice trimmed representation. And that should do it. So let's just take a quick overview. We already saw the receive Bitcoin function. I'll space these out a little bit so it's a little easier to see. And we're driving this console function from main. We saw send Bitcoin, we saw exit console, or we saw receive Bitcoin, sorry. Now we're going to look at send Bitcoin. So let's save this. Let's make sure everything's working properly. Scroll up a little, get this a little bit bigger. And cargo run. Let's have fun with Bitcoin. Sweet. All right, so again, if we try to enter something invalid, cool, still works. And then let's receive because it just feels so great. 6 Bitcoin, rich. And now we're going to send it. Who do you want to send Bitcoin to? And there's our choices. Let's go with Homer. How many Bitcoin do we want to send to Homer? How about 2 Homer? You sent 2 Bitcoin to Homer. Awesome. Awesome. And now one thing we just want to do is we can do that amount trim. You can see why we've been adding trim everywhere. Oh, whoops, that's the wrong thing. Because it often will come up like this with broken lines based on the entry. So we'll add trim. We'll try that one more time. We're going to send to Bart 5 Bitcoin. Much better. Now let's do that again and try to send it to someone not in the list like George. George, not your contacts. Awesome. So everything's working properly, and that is pretty much how you build a basic program in Rust. And we covered a lot of stuff already. We've really only scratched the surface, but there's some really good nuggets in here. And going forward, we're going to break things down, like I said, in a granular level. You're going to understand everything you saw in here. And if you want the codes available on GitHub, there's a link in the description. But I encourage you to follow along the playlist and learn how to write Rust. Hey guys, welcome back to the Rust beginner tutorial on coding and crypto. And today we're going to be going over the basics. And we're going to go over the basics for the next few videos. So we're going to just do cargo new, the basics, get a new project going. And we're going to start with primitive types and some of the type rules that Rust is going to enforce on you while you're programming. So we'll just leave this as a hello world for now. And so for starters, we mentioned this before in the previous video, but you can't overwrite an immutable variable. So what does that look like? Well, if you do let x equals 5, and then you say x equals 6, Rust is immediately going to get mad at you. So you cannot assign twice to a mutable variable. Pretty straightforward. Next, if you want to overwrite a variable that is immutable, you're going to have to use the let keyword. So let's overwrite that variable and see what that looks like. Let x equal 5, and now we're going to say let x equal 6, and that's completely acceptable. Cool. Moving on. You also can't mutate a variable's type. So if we just do a little mutate type function, and we originally initialize a string, and now just as a little side note, because we're going to be talking about this in a sec, this is not declaring any data type. Rust is implicitly knowing that it's a string. In this case, it's actually a string slice, just because of what you're typing here. But we'll get into that in a second. You can actually declare data types too. But this is going to be a string slice. So if we try to take that value and we try to make it, let's say the length of it, which is going to be an integer, you can't do that. So mismatch types can't do it. And then moving on now, if you want to do that and you want to mutate the type, all you have to do is use that. Oh god, I can't spell mutate. Is use that let keyword again. So we're just going to do overwrite type, let, and I'll do a little copy paste for you guys. So you don't have to watch me type all this out. See? Totally cool. As long as we use let. So basically these 4 examples here are telling us that let is going to be how you tell Rust that we're setting a new variable. If you use the same name, it's going to overwrite it. And this is key to Rust's compiler and the storage of your application, mainly the stack and the heap, which we're going to talk a lot about. And I encourage you to understand sort of at like a technical level if you want a little bit more value of what some of these things are doing for your application. It wouldn't hurt to go and take a look and kind of see how the stack and heap work. Because we're not going to go into super good detail on that. We're going to just talk about how it relates to Rust. So anyway, as I mentioned, we haven't actually declared any data types yet. This has all been implicit. So every time we've done this or this, Rust knows by what we're typing there what to set this variable equal to. So you could do it that way. You could code that way if you want. However, a much more common use case is going to be to declare your data types. So if any of you have ever written Java, you're going to know exactly what this is all about. You're going to want to declare your data types in Rust, mainly because it's best practice, but in Java you have to. So in Rust you have the option, but I got to say it's a lot more helpful when you declare your data types, at least where you need to, so you can kind of go through and you can see exactly what each thing is supposed to be, and it helps you prevent those like mismatched data type errors. Just a suggestion. This is what it looks like though. Right in front of your variable, right after you put this colon here, and we're going to make this a U32, which I'll talk about in a sec, and set it equal to 20. So pretty cool. You can do it in line without too much more text. And what this U32 represents actually is this is one of the integer types provided by Rust. So we're going to actually talk about integers. And integers can either be signed or unsigned. So if we do let signed int, and we do I, these are signed integers. You can see it goes 8, 16, 32, 64, 128. Those are all the different size bits you can have for an integer. So I don't know, let's just go with 64 for now, and set it equal to 34. Now, same thing with unsigned. We do unsigned integer, you do a U, and you see we got the same options for bits. And we'll do U32, and we'll make that equal to 11. So cool. That's how you do integers in Rust. Booleans are actually pretty straightforward as well. If you've ever done any kind of programming before, it's very, very similar. Booleans are kind of a simple kind of design, but the one thing to take note of here is Rust actually uses the lowercase kind of representation here. So some languages have a capital T there, capital F for false. Rust is going to do lower. As so. Now let's talk about some strings. So if you might have picked it up in the last video, good for you. But there's obviously some complex rules involving strings in Rust. So there's actually a difference between strings and what we call slices up here. So this, where it's declared without any kind of object, it's just a raw string here. That's called slice. So let's create a slice down here. And you saw this already. If we just go ahead and do this with an inline string here, this is a primitive string, this is a slice, like we said. If you want to declare the data type, it looks like this. Now, don't worry about the and sign just yet. We're going to talk all about that and borrowing and referencing in the next video. But for now, just think about it like this. This is how you represent a slice if you want to declare one as a variable. And then if we say let some string, and we set the value equal to string data type, we're going to do string from, and we'll do donut again. So super important. This is a slice, and this is a string. Awesome. So as you can see, that can be kind of tricky because if you try to do operations, some operations like comparing and different things like that, you'll get a data type mismatch error. Even stuff like print behaves differently. And so it's really important to distinguish between those two things. And as we go further in these tutorials, you'll see plenty of that and you'll understand exactly what I mean. So the last thing we'll cover are going to be constants. This is how you declare a constant in Rust. And wherever you declare it determines the scope of the constant. So we're just declaring it here without being inside any kind of function. So it'll be available to the rest of the program. And I'm going to make it a U32 and go with 20 again. So that is really it for primitive types right now. In the next video, we're going to talk about borrowing and we're going to talk all about this and symbol and talk about some of the magic of Rust data types and some of those rules that we covered here. So thanks for watching. Hello, everybody. Welcome back to the Rust beginner tutorial on coding and crypto. So today, as we promised before, we're going to be talking about borrowing and references and dereferencing, which is kind of like the penultimate rule in Rust, like one of the biggest things that sets it apart from other languages.
Obviously, I know all these things. I'm just watching the videos to get a reminder of the stuff. The more repetition, the better. And because it might say something that I don't know or that I don't remember.
Sure, we've got variations on different data types, different object styles, ways of like writing certain syntax, but this concept of references is going to be the difference maker, the number one reason why Rust stands out. So we're going to dedicate a whole video to it right now, and we'll start by demonstrating what is a reference. So we'll just do an example function here, function references. Now, you've seen this operation before, but let's set this original value as I32 equal to 20. Okay, so nothing out of the ordinary here. Now, we've also teased this a little bit. Let x equal reference original value. Now, what does this mean? I alluded to this in a previous video, but what this and sign means is we are going to borrow the value. So to borrow a value, you conduct a reference. So I'm just going to put the and sign is a reference, and when you reference something, you borrow its value. Pretty straightforward. So I'll add that in comments as we go. Borrow the value of original value. Now, to understand borrowing, we have to take a look at how the memory works in a typical application, especially a Rust application. Now, this is my very haphazardly thrown together diagram of a stack and a heap. So don't worry about all the intricate details. I encourage you guys to go take a look at how the stack and the heap work to get some more context. But I'm going to give you a quick overview here so we can understand how this relates to some of the stuff we're talking about with Rust. So first of all, the heap is going to be where most of your application's data is stored. That's where the main memory is allocated, and that's for everything in your program. So what Rust does, in most languages you have what's called garbage collection, and the program will routinely check to see what objects or variables or what have you are no longer being used, and it'll delete them from the heap to create more memory. Now in Rust, this is not done automatically. You need to specify that. So when we're doing things like referencing, if we take the original value that we're referencing and we destroy it, which we'll talk about in a sec, then the heap space that's allocated for that object is completely freed up. If you change an object, mutating it, things like that, you're going to create new space on the heap for that object and free up the old space. So it's going to change on the heap. And the stack is just a series of pointers that point to the locations on the heap for your different objects. So a basic example, if you create a string is an object. So it has a value, but it also has a length. It also has like what kinds of byte representations each character are, what order they're in. Like there's a lot of attributes of a string, which is why it's represented by an object and not primitive. So when you have something like a string, you have a pointer in the stack that will point to the heap that contains the area in the heap that contains the information about your string. The reason it's set up like this is because the stack is much faster to navigate. It's first in, last out, but it contains only pointers. So it's very, very quick to kind of like parse over, and then you just grab the pointer you need, and it points you to the object and all of its attributes. That's what the application does at a very low level. Now, how that relates to borrowing? Well, as we said, each object and data type has its own location on the heap. So let's go ahead and flip back over to our example here. Now, when we're borrowing this value x, we're borrowing the original value and set it equal to x. What we're saying is we're telling Rust, don't create a new space on the heap for this original value. And typically when you see this is when you're trying to reference a value from like a different scope, like if we had like a for loop going here, or even if we just created a block scope here. Basically, this is a new scope, and each time you pull an object into a new scope or a new function, or you do something to an object, like I said, you're gonna end up with new heap allocations and thus new pointers. The reference capability allows you to tell Rust, hey, don't do any of that. All we need is the value. So when we have like a string, like if we set original value equal to a string, and we set string from Dan, I don't know, some guy named Dan, and then basically what we're saying is all we need is this slice Dan. We don't care about the length of the string, we don't care about the byte values of the chars, we don't care about any of that. All we need is this particular value to conduct our business here. So Rust is gonna say, all right, sweet, like you don't need to actually go create all this new space. Sounds awesome. Now, this can be kind of tricky because you have to be careful about what you do with a variable that's referencing another variable's value. So let's take a look at what that kind of looks like. We already set original value to be mutable. So if we go ahead and say original value equals, and we just change it to a new string, we'll just go with like Josh. Now that's perfectly simple because we've already told Rust that this value is mutable. We can change it anytime we want. Awesome. Now, what if I try to do this? What if I try to print out x? Well, immediately we get a value error here. Cannot assign to original value because it is borrowed. So that's super important to remember. We originally declared this value to be this string, and whether or not it's mutable doesn't matter in the context of referencing. Like you're responsible for that. Rust is going to do that everything for you. It'll throw these errors and stuff, and if you've got a good plugin, you catch it before you run it. But like it's up to you to remember and to see these things and take care of the order of your references. So here we told x to point to reference original value, and it was equal to Dan. Now right here, when we change that value, we have now freed up the original heap space that was representing the string of Dan, and we created a new heap space for the string of Josh. Now x is not pointing at just the value; it needs to go through that stack first to go to its location on the heap. So x is really pointing to the stack pointer. And since we went and changed our heap space, this pointer no longer points to a valid entry anymore. Like the pointer that we were referencing here has now been freed. So you can either have completely freed up space in the heap that this points to, or something totally different. So Rust is going to call you on that every time. It's going to say, hey, you are done with this value. Like you can't do this anymore. Now we can also try something like, all right, well, what if we just let x equal reference again? Now that's cool, but that's because we're telling Rust, okay, reference it now after it's been changed, and now we're going to get that new pointer, and it's going to direct us to the proper location on the heap. Now we talked about what happens if we change a value, and we quickly mentioned destroying value. So what does destroying value look like? Well, it just looks like this. We mentioned that there's scopes involved in these heap allocations. So if we just create this destroy function, and we have it taking a value that's going to be a string, and all we do is have it print out that string, that val, then technically what's happening is when we go and pass something from one function to another in here, we're moving it to a new scope, and that's going to change the heap allocation. So check out, if I go down here and I say destroy, and I pipe in original value, nothing wrong with that right now. But if we try to go ahead and print x again after we pass it into destroy, you can't, because this value has moved out of scope. So the heap has changed, and we don't know what in this function that is going to be represented as, especially since we're not saying equal anything, we're not getting return. Like this is called destroying a value, we're moving it out of scope, and Rust can't determine or guarantee that this reference is still going to be valid, it's still going to be the same as what we set up here. So pretty important to note. I know it's a lot to unpack, but as we go, and as you see this and sign pop up more, and as you use references a lot more, and you can kind of read these errors, and they're pretty helpful, you'll understand a lot more of like how to prioritize and how to organize your references and make sure you don't get tricked up on this kind of stuff. And by the way, the ability for us to be able to check this kind of stuff, it comes at compile time, and it's called the borrow checker. That's what's going to generate these errors, and that's what's going to just take an initial look at all of your references and make sure that everything's in line. So you can leverage that borrow checker to really make sure your code is solid. Now, we did references here, but we also briefly mentioned dereferencing. So what is dereferencing? Well, I'm quickly just going to add a note here and just say object is, quote, destroyed when it leaves scope. And now we're going to talk about dereferencing. So what is dereferencing? Well, as you can kind of imagine by its naming convention, it's sort of the opposite, like the reverse operation of referencing. So what this kind of looks like, the best way to kind of describe this, I guess, would be we're going to do two integer values. We're going to do let a equal 1, and then we're going to let b equal a reference to a. So we're just referencing that value like we did above. And now I'm going to just do an assert function. This is just a test in Rust. So we're going to assert that these values are going to be equal. So you can use this to do tests in your code. So I want to make sure that 1 is equal to x. And we are in a, I'm sorry. And we set this up here equal to a. So that should come back true. We just saw we didn't do anything to it. And now what about b? Well, that'll work. But if you just add this key right in front of it, just add an asterisk right in front of it, what we're actually going to check here is going to be the original value. So this is called a dereference. So what that, I'll comment here, this dereference b is equal to a. So that's a little bit tricky, I understand, and you're going to see this in some use cases in the future, so it'll make more sense in some of the future videos, like especially when we get into like iterating over vectors and over arrays. You're going to see how powerful this really is. But the gist of it is that when you dereference a value, you no longer are referencing a, you are now a. So we're going to assert 1 is equal to a, and we're also asserting 1 is equal to a here by dereferencing b and assuming a in its entirety. Cool, so that's a dereference, super awesome. And there's a couple things I want to mention quickly that are sort of related to this. The first is going to be what's called a static value. So a static value is kind of a neat feature in Rust, and what it basically means is it's a value that basically lives for the entire duration of your program. So you're basically telling Rust, like, hey, don't worry about tracking the lifetime of this value. We're going to set it equal to static. It's never going to expire. So up here when we're referencing stuff, whenever we go to destroy something, like that is the end of life of that value. Anytime that the heap is changed or just freed up and not really reallocated, that is the end of an object's life. With a static, that life is perpetual. So to define static, we're going to just say let x, and we're going to let it be a string slice, and we're going to call it Dave. Now you haven't seen this before, and there's obviously a bunch of errors being thrown because Rust doesn't know that this is going to always be the same length. But when we incorporate a static call, like we talked about, suddenly this becomes okay. Because we're declaring this, it's going to be static, it's not going to change. This particular representation of x here isn't going to change. So let's see what that looks like. If we set y equal to a reference on x, and then we do that same destroy function, and we just do x to string. And now if we try to print out, like we did earlier, the value of y, which is referencing x, you see that suddenly we don't have this error anymore. Up here we get this error, but down here we don't. And that's because this is static. It's not being destroyed here. So I'm just going to say x is not destroyed here. So this can kind of complicate things. You got to be careful with statics because this can go into this function, and if you returned it as something, you could possibly change the heap location. But typically what's going to happen is you'll just create a new location. Like this won't change. You have to do certain things to actually determine the end of life of a static value. But for the most part, this is what's kind of designed to do. I would use it at your own risk for now. It's something we're not going to cover in too much detail in this tutorial. Maybe in like more advanced topics in the future. But I just want to cover it real quick in case you see it in this playlist. Anyway, there's one more thing I want to cover since we're on the topic of memory, and that's going to be the usize data type, which we didn't cover yet. So I'm going to say function usize example here, and we're going to talk about what is a usize. Well, a usize is another way to declare an integer. But the interesting thing about usize is it's actually dependent on the architecture of your operating system. So we'll talk about that in a second. I'll just show you here. If we just let x be a usize type, and we set it equal to, like, let's say 2, you can see that that's perfectly acceptable. It's a valid data type for an integer. And like I said, it depends on your OS architecture. So whether you've got like an x32 or an x64, basically what this data type is designed to do is it's designed to give you the guarantee that there's going to always be enough space in this representation to hold a pointer, like we talked about on the stack, for whichever size your pointer needs to be, whether it needs to be a certain size pointer for x32 or a certain size pointer for x64. That's basically the gist of it. And the number one spot you're going to see usizes is going to be in like indexes and in lengths and in stuff that's going to describe objects on the heap. The nice thing about usize, obviously, you can just use it as a declarative type, and it's irrelevant which operating system this program is actually being run on. So that's pretty neat. Figured since we're on the topic of memory, I would mention it. Now, that's about as far into the rabbit hole that we're going to go on memory and on Rust's like garbage cleanup type rules. So hopefully this was enough to kind of give you a good overview and give you a good introduction to references and some of the rules around Rust memory allocation. This stuff's going to come up over time repeatedly as we do more examples and as we get into some example applications. So as with everything else that you're seeing for the first time in these videos, things will become clear as you see them in practice, as you see use cases and you can think about it logically. So appreciate you watching and check out the next video. Hello and welcome back to the Rust beginner tutorial on coding and crypto. So today we're going to be talking about some basic operations in Rust, mainly functions, conditionals, and loops. So you've already seen me work with functions quite a bit, and we've even touched on conditionals before, but we're just going to put it all in one place here, flesh out a little bit so you have it for reference. So the first thing we're going to cover is function returns. Now, this can be done in a couple of ways in Rust. So let's just do like function give me slice. We're going to tell it that the return type is going to be the static string slice value. And you can remember that from the last video that we did on borrowing and references and things like that. So we're just going to return pizza. So one thing that's super important to note is no matter how you do your return, whether with the keyword or any of the other methods that we're going to go over, you want to omit that semicolon. So super important detail right there. But so this is one way to do it. Whenever you have a return value, you have to declare the data type that this function's going to expect. So here's going to expect a string slice, and we're going to write another one that says give me string, and that one's going to, of course, expect a string. But now let's do this a little differently. We could do return string from pizza, or we could just simply omit this return statement. Since we don't have the semicolon here, we can just write this line like this, and that's our return. So it's kind of like a shorthand. And then you can even go so far as to do something like this, which is more of the same of what we just did, but in a very like stripped down sense. This is totally acceptable too. So you don't even have to declare any kind of variable or anything. You can see we're just returning the number 4. So depending on your use case, that might be pretty convenient. So a lot of flexibility with returning values in functions. Now let's move on to conditionals here. So you guys definitely saw me do this already, but here's an official representation of conditionals in Rust. So if we just say let number equal 3, we can say if number is less than 5, print true. Now we're also going to say else if number equals 5, print, I don't know, like okay. And lastly, else, meaning if it's less than, we're going to print false. And these are just arbitrary values. But that right there is conditional. So like I said, you've seen it before, but they do make it pretty easy. It's very similar to, it looks similar to like a combination of like Java and Python, if I'm being honest, but not super verbose. Loops are even cooler actually. There's a lot of nice built-in functionality for loops in Rust. So let's take a look at, we'll start with a while loop. So a while loop is actually pretty simple to implement. One of the more simple ways to do a loop. You can just do the word loop. And then let's just do like print line again. And this is going to be an infinite loop. So just a little warning to the user here that this is an infinite loop. But yeah, this is a while loop right here. So obviously if you want to add logic to break out of this and stuff, or you want to have a counter or something, that's what you would probably do. But this will run forever unless you break out of it. How about a for loop? Well, a for loop is done a little bit differently. So you don't use the loop keyword for loop. You still use for, like you've probably seen in other languages. And let's just say for n in range 1 through 40. So that's a pretty neat thing right there. Rust lets you define a range just like that, inline, without having to call in any kind of like function or embedded method or anything that will generate a range for you. It's part of the structure of the language. So that part I think is super neat. And then we're just going to do like, let's just do like hello, number, whatever. And we'll obviously just plug n into that. So cool. And the last type of loop that we're going to cover is we're going to cover a loop that can actually be stored as a variable. So this is kind of cool. You can set a variable equal to a loop, and then whenever you break out of the loop with and return a value, that's what's going to be set to that particular value. So that might be a mouthful, but let's just take a look at what that looks like in practice. So we set our counter equal to 0 to start. Now we're going to let g equal the loop. And inside the loop, we're going to just say if the counter equals 3, we're going to break out of it. Now, instead of going like this and just saying semicolon for break, I'm actually going to go ahead and put these curly brackets here, and we're going to return that donut slice. And then we can't forget to add our semicolons in. But this is going to, obviously, when this counter hits up to 3, it's going to add this donut value as the value of g. So super cool. And this is, you can probably already think of use cases where this is convenient, but don't do something like I just did. Make sure that you add some kind of incrementing function here. And then you'll actually have this counter going up. So you're good to go. So this was a really good once over of some basic operations in Rust. In the next video, we're going to see collections and iterating. So we're going to look at things like vectors, which are similar to lists. And we're going to look at arrays. And we're going to see how Rust offers different ways to iterate over these kind of like collection objects. So that'll be super helpful, and some of this stuff might even tie in. So stay tuned. Thanks. Hey everybody, welcome back to the Rust beginner tutorial on coding in crypto. So today we're going to be talking about collections. We're going to talk about tuples, arrays, and vectors. We're going to take a look at how you can iterate over those objects. So to start, let's start with the tuples. So tuples are pretty simple in Rust. You basically just use the parentheses to declare them. So we're going to say let tup, and this is how you tell it what the types are supposed to be. Put up the parentheses. We're just going to do 2 signed integers, 32 bits, and a string. We'll set that equal to 1, 2, and string from Paul. Cool. So there's a tuple. So if we just did like print line here, whoops, I'll show you how you can access those values in a tuple. So 2, and then to access the index of the tuple, just do a dot. And you can see they come up here in Visual Studio Code. So we'll just go ahead and print each of those, and these dang semicolons, and we'll just see what that looks like. Go into the basics folder here, and run cargo run. Oops, didn't save it. There you go. Now, what if we wanted to do a mutable tuple? Can we do that? Can we change just one value at a time? Well, yeah, sure. So let's go ahead and just make this immutable. And we're going to go ahead and just copy these down here, because I'm going to print all the values again. But let's go with 2, and we'll change the string 1, so index 2, to a new string, and we'll just change it from Paul to John. So now if we take a look, there you go. So that's how you change the value of a tuple. That's how you do tuples in Rust. Super convenient. And now we're going to move on to arrays. So I'm just going to minimize this a little bit. And if we want to take a look at arrays, they're also somewhat straightforward. There's a couple cool things you can do with arrays. Like you can use them to basically do different operations. And here's an example of a mutable one. So I32. Now when you declare an array, you want to do this bracket syntax here and declare the type that's going to be in the array. They've all got to be the same type. And then you put the semicolon, and then you tell it what the length is going to be. So we're just going to do length of 3, and they're all going to be I32s. Awesome. Now to declare that, you can just put the values in yourself. We're going to do 4, 5, and 3. And I'll show you a couple ways that you can initialize an array without just like manually putting these variables in, or these values in. But either way, since this is mutable, to change a value in the array, you just reference the index like this and set it equal to your new value. So we're going to set both 0 and 1 equal to 0 and 1. Actually, I'm going to do 1, 2, so the array comes out as 1, 2, 3. And then we're just going to do a quick loop over the array, referencing each value. And we're just going to print out each value as x. So we'll change this over to arrays. We'll get a cargo run going. And you can see 1, 2, 3. Nice. Another way you can initialize an array is you can actually initialize with an expression. And this is pretty neat. I love this feature. So you can actually you can declare the array just like we did, right? So I32, we're going to do like a 5 this time. But I don't really feel like typing out 5 whole values. What if I just want them all the same? What if I want them all to be zeros and I want 5 of them? Well, all you have to do is put the brackets up like you did before, type the value you want in each field, and then how many? 5. Bingo. So that'll give us an array of size 5 with all zeros. And I'm just going to copy paste this because I'm lazy. And this will give us a printout of all those zeros. See? So 5 zeros. Nice. Now there's another cool feature with arrays. You can use them to initialize variables. So this is a little bit tricky, but follow along, and I'm sure you'll get it. So we're going to initialize an array, but we're not going to give it a name, right? Like there's no variable name here. We're going to put the variable names in an array itself. So I'm going to put 2 variables called greg and mark in this array structure. And I'm just going to put another array structure here, and we're just going to create some strings. So we'll do greg, to string. And here's another way to create a string that we might not have covered yet. And mark, to string. It's just going to go from slice to an actual string object with that method. Nice. So now what this has done for us is initialize 2 variables using an array. And it's implicitly determined that they're going to be strings. So we can actually print each of these out, but like how do we reference these? Like we said, we don't have a name for this array. Well, technically this array doesn't exist. It was just used here to build these variables, and now you can just access the variables as if they were normally initialized on a single line. See? And so we'll do each of that for greg and mark. We'll take a look at what that looks like. Boom. So kind of a neat feature with arrays. So now we're going to move on to vectors. So a vector in Rust is very similar to a list if you worked with lists before. It's just a collection of items, and they have a little bit more flexibility than arrays. Like an array is very size sensitive. In fact, whether it's immutable or not, you can't change the size without overwriting it. So with a vector, you can. You can append stuff to a vector, and it's designed to recreate its own length in the memory of the application. So pretty neat feature, and you can see in some of these examples we're going to write of that. Like you'll see that flexibility compared to the array examples we just did. So to initialize a vector, this is how you declare the data type. We're going to stick with I32, and you can do it like this with the vec macro, and this is going to just let you type an array, and it'll convert it into a vector. You can also do, let's make a mutable one here. You can also do same data type declaration. You can use this range syntax, and then just do dot collect and make that into a vector with numbers 0 through 10 in each position. How cool is that? That is so cool. Anyways, we're going to copy this loop again. I'm lazy. And I'm going to come down and print out each value in the vector here. Whoops. And so we'll be able to see what that looks like here. Now, obviously, you know it's going to print 0 through 10, but we're going to see what that looks like. And now while we move on, I'll give you an example of appending to a vector. You just do vector.push -2. Now, one thing to know is we made this thing mutable. So if you don't make it mutable, you're not going to be able to push new values to it. That's just straight immutability, obviously. But as long as it's mutable, you can change values.
Probably in the program I did, I used a vector, and would be better to use an array because the size of the thing is fixed. But I didn't know that. I guess I knew that arrays and vectors are different, obviously, but I didn't know that the difference is that arrays have fixed size and vectors are more flexible. So that's a good reminder here. And I should probably use array on the program that I built, but doesn't matter that much
You can change the length of
on
it.
that case specifically.
You know, you can do all kinds of things on there. And since we're pushing there, I'm going to print out the last value of the vector to see what we just pushed down there, right? So our last value right now is -1, and then we push -2 on there. So if we print this syntax here, we do vector, and then we reference the index. Now, if we know this thing for sure is going to be 11, we can put 11 here. But the proper way to find the last index of a vector is to just do the length, vector.len, -1. And that should give us a nice printout of the last value. So I'm going to just comment this out while I run this so you don't get confused, but there goes -2. I always forget to save it. Either way, we got that -2 out there, so we know that that's our last value. So what we're going to do now is we're going to demonstrate pop as well. So we're going to do same print, and we're going to do vector.pop. And what pop does is actually removes the value from the vector. It'll pluck it out or pop it out and return it. Now, right now, Rust is yelling at us because the pop function actually returns an option. So what an option means, and we're going to talk about this in a couple videos from now, it basically means that you can either get a value back or you can get none. And in order to handle that operation, you're supposed to write like the handling, basically how you want to handle the two possible outcomes of an option. But for simplicity here, since we're not going to dive into that just yet, this is a print filter you can add that will automatically recognize that this is going to return an option. So all you got to think of right now is this pop function could return a value, but if our vector is empty, like if you do this on a loop and pop all of them out, you're going to get none. So I'll demonstrate what that looks like, and then I'll even show you. See, like sum -2. Sum is the option return of a valid value. So if we go like this and we say loop, actually it's probably not good. I won't do it never ending loop. I'll do a for x in 0 to 20, so you can see some of the none printouts. So this is going to pop every single value, and as we get past 11, since we're going to have 11 values or 10, this is going to pop us up into the none return value. So you'll see that. See, we get some value each time, and then once our vector is empty, we get none. Cool, nice. So we're going to move on now to, I'm just going to set this back to this so that nobody gets confused if you're looking at the code on GitHub. We're going to move on to iterating. So iterating is pretty neat. Like you just saw the for loop is one way to iterate. That's a pretty traditional way to do it. But there's more robust ways to iterate over these different data types in Rust. So let's take a look at iterating over arrays. So we'll start with just a typical array. We'll just say let r, we'll go with i32 again, 5, and we'll do this all zeros because it's cool. Now, the first way we can iterate over something in Rust is using the built-in function for arrays called .iter. So if we do for x in r.iter, and we just want to print x, we can do that. Now, a couple important things. So obviously, at a basic level, x is going to iterate over the array, and we're going to get each value of the array. But what's important to note is .iter is actually built-in referencing the array. So this is going to be by reference, and I'm just going to do .iter in parentheses. Now take a look. If I try to actually reference the array, it's going to geek out because this is already referencing it. So you don't need to put the and sign in front of that. Sweet. Okay. So now let's take a look at what's called enumeration. So we're going to do the same thing, but we're going to enumerate this. Now already you can see that this is not throwing an error, and that's because enumerate, let's see what Rust is saying. See, it's giving us this tuple here. That's saying that's what x represents. So enumerate is going to actually give you the tuple representation, gives you a tuple, and it's going to look like this. It's going to be the index of the array and then the value. So super important to know, this is extremely convenient because use cases for this come up all the time. We need the index and the value. This is how you do it. And again, since we're using .iter, we're still going to be referencing that value. So again, like we saw in the tuples above, all we got to do to get the value is just reference that tuple index. Sweet. And so now we'll just give this a print and just take a look at what that looks like. So there's our zeros, and obviously we're just printing the values here. But if we want to do like x.0, we want to comment this out, you can see there's indexes. So pretty neat. Now, these two examples that we just went over are by reference. So is there a built-in iteration method for taking the value itself and not just borrowing? Absolutely. So we're going to do by value, and it's actually called into iter. So kind of confusing. It's very, very similar, you know, .iter versus .into iter. But if you can just remember that the .iter is going to be referencing it, and then if you go into iter, you're pulling the value in, so you're not borrowing. So one way to kind of think about it. So we'll do for x in r, and actually I'm going to make this item because we're going to mess with that enumeration a little bit. And we're going to say into iter, enumerate. And then as you saw, it's going to be a tuple. Now you can choose to do both index and value of the tuple. So that looks like this. You can say let I and x, and this time we're using a tuple instead of an array to create these values, same referencing the array. So this
Didn't understand what I said there.
is going to be by reference, and I'm just going to do .iter in parentheses. Now take a look. If I try to actually reference the array, it's going to geek out because this is already referencing it. So you don't need to put the and sign in front of that. Sweet. Okay. So now let's take a look at what's called enumeration. So we're going to do the same thing, but we're going to enumerate this. Now already you can see that this is not throwing an error, and that's because enumerate, and let's see what Rust is saying. See, it's giving us this tuple here. That's saying that's what x represents. So enumerate is going to actually give you the tuple representation, gives you a tuple, and it's going to look like this. It's going to be the index of the array and then the value. So super important to know, this is extremely convenient because use cases for this come up all the time where you need the index and the value. This is how you do it. And again, since we're using .iter, we're still going to be referencing that value. So again, like we saw in the tuples above, all we got to do to get the value is just reference that tuple index. Sweet. And so now we'll just give this a print and just take a look at what that looks like. So there's our zeros, and obviously we're just printing the values here. But if we want to do like x.0, we want to comment this out, you can see there's the indexes. So pretty neat. Now, these two examples that we just went over are by reference. So is there a built-in iteration method for taking the value itself and not just borrowing? Absolutely. So we're going to do by value, and it's actually called into iter. So kind of confusing. It's very, very similar, you know, .iter versus .into iter. But if you can just remember that the .iter is going to be referencing it, and then if you go into iter, you're pulling the value in, so you're not borrowing. So one way to kind of think about it. So we'll do for x in r, and actually I'm going to make this item because we're going to mess with that enumeration a little bit. And we're going to say into iter, enumerate. And then
I didn't know that. So very useful. So the difference is this is for you're getting the reference and this is getting the actual value.
as you saw, it's going to be a tuple. Now you can choose to do both index and value of the tuple. So that looks like this. You can say let I and x, and this time we're using a tuple instead of an array to create these values. Same concept though, still pretty cool. because we want to have two different types. So that's why we would use a tuple here instead of like we saw up here, where we're using an array to create two values. That's because these we know are going to be the same. They're both going to be strings. But down here, when we use a tuple, we can tell Rust, like, hey, one of these, the first one's going to be a usize, and the next one's going to be an I32. So we're going to set that equal to item. And really quickly, usize is a representation of length. It's a representation of index. Like, it's used to determine a number that actually represents stuff that's coordinated on the stack and the heap. So if you watched the borrowing video earlier in the playlist, you kind of understand what this is pointing to. I did reference it in that video as well. So now that we've done that, we can just print out, let's just do like, we'll say index, whoops, and we'll say, we'll make those brackets there, and then we'll do value brackets, and we'll just do I and X. Now, we could have totally done this like we did earlier, but it's a little more clean to do this. And obviously in the typical use case, you'd be doing more than just printing these things out. So it's good to toss them in their own variable for the scope of the for loop. So totally cool. Let's take a look at how that works. Right on. Sweet. So that's arrays, and iterating over vectors is actually very similar. So they iterate the same as arrays. And there's a couple like cool features about vectors that we'll cover too, but just to show you, we're just going to let the vector equal I32. And since I love this range collect guy, we're going to do that. And now for X in vector.iter, we're just going to print line X. So you can see it's exactly the same as the array one. Literally the same. Sweet. And all these are the same too. And it returns the same tuple. It works the same exact way. So what's different about vectors then? And I'm just going to do a quick print line here and just we're going to separate the vectors from the arrays. So what's neat about vectors is you can also do stuff to a mutable vector. Like we covered earlier how you do different things like pushing and popping to a mutable vector. But when you iterate over a mutable vector, you can actually do stuff to it while you're iterating. And that looks like this. We're going to create a mutable vector called mute vector. Use I32 again. And you know I'm going to use this range function again. And now that we've got that declared, we're going to do for X in mute vector dot iter mute. So iter mute actually is going to iterate over a mutable vector and allow you to do things to the vector. So this is what that looks like. Asterisk X. And we're just going to add 3 to each value. Now, what this asterisk is actually doing is called dereferencing. So if you watched the video on borrowing earlier in this playlist, you know exactly what that means. But in a nutshell, this asterisk tells Rust, like, okay, even though X is just like serving as a representation of this value, since we're iterating with this mutability feature, we're going to dereference from X to the actual value in the vector. Like, actually do this function on that thing inside that vector that we're iterating over. So that's all that means. Now, we can print this out, and you're going to see the same like syntax we saw earlier when we printed a whole vector. We printed like a vector pop. We're going to use the same option filter here with that question mark, because when you print a mutable vector, Rust doesn't really know what size it's going to be. Like, you can't predict it ahead of time. So it could be 0, it could have nothing in it, and you're not going to be able to print anything. So this also returns an option like we covered earlier, and I promise that will become clear in a later video. But for now, let's just print this out, and let's see what we get. Sweet. So you can see that we printed out our original vector, 0 through 4, and now each of the values in here are actually increased by 3, because we went and added them there. So pretty neat. Iter mute is a pretty powerful function. Allows you to just kind of simplify things by dereferencing. Super, super cool. In the next video, we're going to talk about options and matching, so you're going to see a little bit more fleshed out details on some of the things we glossed over in this video. So that'll be super helpful. Thank you for watching, and stay tuned. Hello, and welcome back to the Rust Beginner tutorial on coding and crypto. Hello, and welcome back to the Rust Beginner tutorial on coding and crypto. So today we're going to be diving into options and also matching. So these are both honestly some of the coolest parts about Rust, and I'll explain why. So the biggest concept here is Rust does not have null. So there's no such thing as null in the entire language of Rust. There's what's called none, and there's a big difference. So Rust will actually force you to handle the possibility of a null value. If you watched the previous video on collections, you saw when we tried to pop a vector, there was errors being thrown because we had a possibility of there being no values to pop. Therefore, Rust was telling us we needed to implement an option. So, like I said, instead, we use options. Now, this is what an option looks like, but these come as part of the Rust language, so like, you don't have to actually define this. I'm just doing it as a demonstration. So, and this is also kind of a good concept to grasp. This T here represents a generic, and that's outside the scope of this tutorial here, but in essence, think of this as like X, and it's a function. So like you have an option of whatever you're going to pass in. It could be this value, or it could be none, right? In the case of our vector, this would have been our vector pop. Anyway, this is what an option looks like. It's either some or none. So if you want to implement it, let's do a little option example here. It looks just like this. So we're going to go back to our already previously seen vector conundrum. And now that we've got this initialized here, we're just going to create a loop for I in 0.5 range. And we're just going to try to do that same thing again, right? We're going to just try to print, and we're going to try to pipe in vector pop. Whoops. And you can see that we're going to see the same error we saw before, but we didn't really read this last time. So what's actually happening is this value that we're trying to pipe into the string to print out is actually an option. It's not whatever's in our vectors. Like here, our vector is a bunch of integers. This is an option. It's either going to be some integer or none, like we talked about. That's why when you saw it printed out, it looked like this. It looked like some and it looked like none. That's because we put this option filter on the print statement, and that just prints the actual option itself, like the enum, which we'll cover. But the correct way to actually do this is to handle that possibility of a none, to handle that option that you're going to get back from this function. So what does that look like? How do we get rid of this? Well, how do we get our actual value really is the question. So what we want to do is we want to go like this. We're going to say let x equal, and so originally we want it to be equal to vector pop, right? Instead what we're going to do is we're going to say match. Now this is the match keyword, and this allows you to match possibilities within a value. So it's very similar to a conditional, or if you're familiar with a switch case, but these are really slick, honestly. So check this out. We're going to match vector pop. And since it's an option, it has multiple possibilities. Like we know this up here is an option. It's an enum. We're going to do sum, and we're going to set up a lambda expression. So you can just use whatever kind of representation you want for the value. Let's just use like val. And if it is some value, like something is existent from, like something is returned from this, then just give us that. Give us that value. If it's none, give us a 0. Close that out. And then within our for loop, we're going to just do print line. And now you'll see we can just use x. Sweet. So like I said, this is part of Rust's internal library, so you don't need to actually define this. I'll just comment that out so you can see that. And then we're going to run this bad boy. Get open a new terminal. We're going to slide into our project and do a cargo run. See, we get 3, 2, 1, and now all of our values have been popped out after 1, so we get this 0 back. Sweet. Awesome. So that's literally options. This is what Rust wants you to do to handle whatever it is that might throw a none. And these are pretty expansive. Like, you can create whole expressions in here and point to different methods and what have you. So definitely explore that a little bit. Now let's take a closer look at this match function, because this thing is super nice. So let's create a new function called match this, and we're going to actually pass in a variable called val, and it's going to be an i32. And let's just expect a string to come back. Now all we need to return is the result of a match statement. So again, we're just going to use the match keyword. We're going to match val, and we're going to say, okay, we know we're getting an i32, right? So what we want to do is say, all right, 1, give us the string 1. And then I'm just going to add this to my clipboard. A use case for if there's nothing there is obviously going to be outside the scope. Hello and welcome back to the Rust beginner tutorial on coding in crypto. And here we're going to be talking about structs. So structs are a way in Rust to represent an object. So they're very similar to classes. You can define attributes of a struct. You can define methods, which are just like functions that are part of that object. And there's a lot that you can do with these kind of data types. So obviously super, super important for any kind of object-oriented programming. So the way that you define a struct is you just use the struct keyword, and we're going to just call this one user, and we're going to add some attributes. So when you add an attribute, you're going to have to provide the data type. So we're going to go with username, email. Those are both going to be strings. Then I guess we'll just count like the number of times somebody signed in, and we'll determine if they are active with a Boolean. Cool. So that right there is how you define a struct. Now, if you want to use it, you have to initialize it. And you have to actually initialize it into some kind of variable or, as part of an operation or what have you. So we're just going to initialize it as a variable. So we're going to say let user1 equal user, curly braces, and now we're going to determine each of those attributes. So let's set the email to, I don't know, like someone at example.com. We'll set the username to some username, 123. And as you can see, it doesn't matter the order, right? Like we started with username and then we went to email. Like you don't have to determine the order or follow that order. You can just, since you're using the keywords of the attributes, it doesn't really matter. Active, we're going to say true. And how many times did they sign in? I don't know, once. And now this user1 is of type user, and it's going to have all these attributes that we presented here. Cool, nice. One neat function with structs is if you wanted to initialize it, let's just say initialize struct, simple. If you want to initialize it and your function actually is using the same like keywords, the same variable names, you don't have to actually declare the attribute name. So I'll show you exactly what that means. If we explicitly say that we're going to get username and email as strings in our function, and then we want to go in and say let user1 equal user, originally what you saw was we did email and it would look like this, right? Like we would have username, and it honestly just looks kind of silly. So what you could really do is you could just do something like this. We'll just comment that out so you can see it still. User. And really nice. Comes in handy, and you can definitely think of some use cases there. So what about methods? If you guys are familiar with classes, you obviously know about methods. So let's talk about how those work. I'm going to use the rest of this page here for this, so I'm going to space this out a little bit. But let's introduce a new struct. We're going to do person. And that person
I think he just talked about how you can put this object into this one. I'm just gonna add the ones that are not included in here. I remember watching this video.
It's going to just have a first name of string.
I think I'm gonna go fast
And a
over
last
this
name of
one.
string. So in order to implement a method for this person struct, traditionally what you'd see in a lot of languages is like these sort of curly braces are going to represent the scope. And inside you have to pass an example down here. So the result of our details method and get George's name, right? Like we told it to return the last name. So this is going to print out Lopez. But what if we instead, let's say we write a new function up here and we want to say, I don't know, let's do like function more details. And we'll do the same thing. We'll just have it return a string. So what is an associate really for like code organization and things like that? Like if you have that are just type this representation and then do George.more details. And the name. Hey guys, welcome back to the Rust beginner tutorial on coding in crypto. And today we're going to talk about enums. So you got a little taste of enums in the last video, right? We talked about options, and we said that options and match were some of the coolest parts about Rust. And options are an enum. So what does that make enums? Enums are super, super powerful. And a big part of Rust actually relies on enums. So we're going to go into some detail here on how you use them, and we'll also give like a high level overview of exactly what they're doing in a memory sense. So first, to define an enum, like you saw, we're going to create this stoplight enum, and we're going to have green, yellow, and red. And now we talked about the match function or the match keyword in that last video, and you saw with options how you can match. And like I said, you don't have to handle like a wildcard case or like a not match case because enums have a definite list here. There's only these amount of values it could be. So if your function is expecting an enum, like if we write read light and we say that we're going to get this variable light and it's going to be of type stoplight, which is an enum, then your match case knows like, okay, there's no way that if we get an enum, it's going to ever be anything besides these because that's not possible. Rust wouldn't let it get that far. So what we're going to do is we're going to match this entry, this light value, to whatever kind of type of enum that we get and return some kind of value. So let's just return a string. And then we're going to say, all right, match light. And now we want to take a look at the possibilities that this could be any of those values. So what we want to say is if it's stoplight green, then we're going to say go. It's a string. And I think you can guess what we're going to do here. But if it's yellow, we're going to do slow down. And If it's red, yep, you guessed it, stop. So pretty cool. Now that's all you have to do. And like I said, because Rust knows that it can only be any of these values, you've already bound it to the possibilities that are represented by this enum. That's an integral part of memory management and of handling like nulls. Like there's no null in this situation. Like this function can't see a null. So pretty neat. But anyways, right, let's print this out. Let's go with the, I like to keep all these functions separate so I can just copy it onto GitHub for you guys. But let's do our read light function. And see, it's already telling us like, hey, make sure you put in this enum here. We're going to do stoplight green. And of course, we're going to print out each of those and run this guy. And we'll see what that does. Slide into our guy again here. And see, we get each of those things. So that's how you can use an enum and a match to kind of like dictate different things about your program. And again, this is another thing that you can expand on. Like you can make these be full functions and expressions in there, not just like return values. So there's a lot you can do there. But enums can actually get a lot more advanced than this. This is what's called a unit type enum. And at a high level, what that means is basically this like English word, like this human readable word, doesn't mean anything to the compiler. It's just so you can represent it with your code. But there's an underlying value behind these that points to different parts of the memory of the app. And without going into like excruciating detail, these are just like representers. And they enable you to write stuff like this in a nice, simple way. Now, what we're going to look at is a different type of enum where you actually have things like functions present in the enum. You have like structs that can be in these places here. And then it works with the memory a little bit differently. So we're going to take a look at how these are written. We won't dive too much into the memory stuff. I'm not trying to slam you guys in a beginner tutorial, but we're definitely going to see these things in practice. So let's go ahead and create some space here and talk about advanced enums. And this one's we're gonna have a little fun with this. We're gonna do a golf event enum. So the first event we're gonna allow is a tee up. And like we said before, this is a unit. And it's gonna represent the golfer is teeing up the ball. So there's really no like values or anything involved. It's just something that's happening. The next type of event we're gonna have is the golfer's drive. And I'm gonna keep all of these data types as strings because it's kind of a pain to get them into like a printable statement. I don't really want to get into all that messy stuff. I want to really just demonstrate the enum. So you're gonna see strings here, but you could do integers and stuff too. So if we're gonna drive here, that string, we're gonna have this function really. And it's gonna allow us to basically build functions on the enum and pass strings into them. And we're gonna be able to say the golfer drives the ball n yards. And then our last enum option that we're going to have is a club select. And this one's going to be a struct. So we're going to just do an inline struct here, where we're going to have a club as a string, and we're going to have the max yardage that that dude hits on that club as another string. Cool. And we'll just define that real quick. Struct. The golfer selects a new club. So this looks pretty wacky. And you're probably wondering, okay, what does any of this even really mean? Well, let's see it implemented with a match, and you can kind of get a better glimpse of what's going on here. So if we just do like, let's do golf event as the function name. And let's say we want to pass into this function, just like we did up here with the light. We want to pass into here a golf event. And we want to get back a string, just like we did before. Same kind of a setup here. So match event, like earlier. And we're going to define what's going to happen for each of these golf events. Now, I'm going to copy these in real quick so you guys don't have to watch all this. Now, don't worry about initializing these ones just yet. We'll get down there. Let's start with the tee up. So there's no values or anything involved. It's just a unit type, just like we saw up here with the light. So we're just going to return some kind of like generic string message. Like we're going to say the golfer is teeing up the ball. And of course, we'll do that to string guy. And now for the drive, this is where things get kind of interesting. So we're going to write a little expression here that's going to say, all right, we're going to input the amount of yards as a string, and our string that comes out is going to look like this. And you can see what we're kind of doing. We're just kind of creating a nice concatenated string here. Oh, forgot a space right here. So cool. Now we're going to actually build a function based on this right here. We can pass in this value yards, and we can get what's going to be printed out here for the yards. So we're going to do something very, very similar with the struct as well. So let's see how we initialize this guy. So we're going to do club, and then just like we have above, max yard. And we're going to say golfer has equipped, copy this again. And this is again going to be kind of messy, but I'll try to get through it quick. And so he's equipped a club, and the max yardage he's hit with that club is going to be that max yard value. Nice. All right, nice. So there's obviously more complicated things you can do with a struct in this situation. This is a very simple example, but ideally you would have an object with attributes and stuff like that that you'd be able to do things with in here. So kind of cool. But all right, so let's see this in action then. We're going to write another example, and we're going to say match golf example. And this is where we're just going to like print all these. So just like above, I'll actually copy them, try to save you guys from that a little bit. So instead of this, obviously we're going to do golf event. See, telling us again that we need to have a golf event. And copy these all in here. The first one we're going to do is, of course, the tee up. So golf event, tee up. The next one we're going to do is a golf event, and we're going to do the drive. And right here is where we're going to tell our function that we defined up here just how many yards this person's going to hit. Let's go with like 250. Sweet. Now, and we're going to have to obviously put this to string. Trust me, it could be worse. This is already messy, but it could definitely be more messy, trying to go from numbers and stuff. But anyway, so we're going to obviously see what that's going to give us to print out. Now, same thing goes for the struct one. We want to just create that club select struct, and we're going to go ahead and pass in the value for club. We'll go with 6 iron. And, oh, that's 2 string. And then we're also going to do max yard is going to be 175 with the 6 iron. That seems reasonable. Cool. All right. And now we're just going to print that example out here, like we've done before. And there you go. We get our 250 that we piped in here, and we get both of the values that we put in to the struct. So kind of neat. That's how you can use enums. Like basically what we have right here is we have a function, a match function, that is built on an enum. And now we can just pass enums into that match function, and we never have to worry about null. So that's like the biggest lesson. I'm going to quickly talk about one other aspect of enums that's kind of sweet. Enums also have methods, just like structs. So let's just quickly do like a basic enum that you can probably see just about anywhere. We're going to do forward and backward, and then use attributes and stuff with enums. It's a little bit complicated, like how you filter there. Direction.walk. Now, if you remember from the previous situation where we tried to have this, be the same kind of thing with an associated function, like we did run here, we're not allowed to do that. Instead, this is an attribute of the enum, not the object created by the enum or with the enum. Cool. And obviously, we're just going to do this as a parent, and we'll see that in action. See? So that's pretty cool. Enums are definitely pretty cool, and if you can really get good at these, you're going to have an easy time programming in Rust because you'll avoid a lot of headache with unexpected values and things like that. Thanks for watching. Hey everybody, welcome back to...
It's still hard for me to understand enums, but I'm sure at some point I'm gonna get it. But it is a little bit confusing for me because I don't have a lot of experience. Struct and implement, I think I get it. It comes more naturally, probably because struct is kind of like an object in other languages, and then implement is kind of like a class. But enums and the types and lifetime, I think it's kind of hard to understand.
The Rust beginner tutorial on coding and crypto. So if you made it this far, we've covered a lot of really great basic topics. And now we're going to actually build something. We're going to build a sample application, much more robust than the first one we did. That's going to encompass a lot of that stuff that we've seen in this tutorial. So what are we going to build? Well, it looks like this. We're going to build a little blockchain querying app. So we're going to look up information from the Bitcoin blockchain, and we're going to do stuff with it and come up with some, conclusions in our Rust application. So you can see here from this diagram, this is what our app is going to do. We're going to figure out what chain we're using from the Bitcoin blockchain. So is it the mainnet? Is it a testnet? Like whatever. Then we're going to look up some information about a particular wallet address, and that's going to give us all the transaction hashes that wallet's done. So then we'll look up each of those transaction hashes, and finally, we'll use all that information to calculate that wallet's current balance. So it'll be super cool. You're basically going to be doing a parsing of the blockchain to find out how much Bitcoin your wallet has. And if you have a wallet that uses the same address every transaction, then this thing is extremely accurate. It's all on the network, so it's going to give you that return value. So pretty cool. What you're going to need to do this is obviously you're going to need a Bitcoin wallet address to look up, to plug into this thing, to get some information about. So you can create one, you can use one of your own, and we're going to actually protect the wallet address and API key in a certain way to use environment variables in Rust. So I'll show you that. So you don't have to worry about this getting off of your computer. But anyway, so the way we're going to query the Bitcoin blockchain is we're going to use an API called NowNodes API. And so all you have to do is go to nownodes.io, and you can get a free API key just by putting in your email here. Like I've already done this, so I'm not going to do it right now, but it's that easy. They'll just email you an API key, and it's free to use, and you can look up all kinds of information on the blockchain. So once you've generated an API key, if you know how to use Postman, this is super easy to use with Postman. If you want to test this out, if you want to explore this API some more, all you got to do is go to Docs, and then click Run in Postman. And what that's going to do is that's going to actually download the collection, which you can see I have right here, to your Postman app, and you'll be able to use all these different requests. And you just go into the group here, and you just put your API key in just like this. You write API-key and put your key right here in the value section. And that will give that authorization to everything in this group here. So all of your requests here will be able to inherit this auth. And you'll be able, and don't forget to set this API key. And you'll be able to use all these different GET requests and see what's going on the chain. So to start, just to show you what this is going to look like, if we hit the status endpoint, there's no payload or anything, we just hit GET. You can see it gives us information about the Bitcoin chain. So what coin are we using? Bitcoin. And then if you scroll down, what chain? Main. So we're going to get some information from this request to talk about like what chain we're on. And then you saw the next is we're going to look up our wallet address stuff. So if you just put in an address up here in the URL, you can get back information about your wallet. And there's this little example wallet I have. And here's 3 transactions that I've conducted. And so with these transaction hashes, we can actually go to the get transaction, plug it in up here, and hit it. And you can see it'll give you the whole transaction or it'll give you the block that your transaction is part of. So super cool. And these are the 3 endpoints that we're going to use in our app here. So feel free to download this collection and to mess around with all this stuff. There's a lot of different endpoints in here. There's 2 different APIs actually. So go crazy. But we'll come back to this Postman screen a few times as we talk about like what we're doing in Rust. So let's dive into the code. So now we're back here in Visual Studio Code again, and we're using the same project that we had before. You can see our previous 2 applications in here. And of course, what we're going to do is we're going to do cargo new, and I'm just going to call this thing blockchain info app. So we'll generate that new cargo project. You can see it was created up here. And now we're going to take a look at how we start building this thing. So the first thing we're going to do is we're going to actually pull in a few dependencies that are going to help us do a few things with this app. So first of all, you're going to need dependencies to make REST requests. Like we're going to need some libraries to be able to hit those endpoints from NowNodes and get the information back. So what that looks like is we're going to put these 3 dependencies in here. And just so you guys know, I'm going to copy some of this stuff from my GitHub. The code is...
Oh, so the code is on the GitHub. Maybe I should just copy the code from the GitHub. Version. Oh, there's a thing there. Oh, there we go. I think the version might be incorrect. That's why I'm getting the warning there. I don't get why though, because in my mind it should work with previous versions, but yeah. Oh, there you go.
Is available on GitHub in the description. The link is there. Feel free to take a look, and you can even copy paste some stuff as we.
I'm probably not gonna have time. Yeah, 3 minutes. So I think what I'm gonna do is watch all these 3 videos off stream and copy the code from his thing, and then
we go.
next time I'm going to go based off his code and try to, not try to, do the thing that I wanna do, which is get data from Ethereum and analyze the data. And then after that, I'm gonna see how I can get data. I'm gonna study how I can get data from Solana. And I wanna finally, after that, go back to the chain data stuff. But I think I'm gonna be focused more now, not on the website part, but on just analyzing the data, displaying the data, and seeing what is possible to do or what kind of conclusions can I have with the data. I think that's a lot more interesting. And then from that point, I'll think about whether or not I want to continue to develop the website. Because the website is something that I did more for the build space stuff, but I think the more important thing and the thing that I'm more curious about and focused on is understanding the data from the blockchain and associating that data with human behavior. That's my main goal. So
Go if you don't feel like typing everything out, because some stuff is going to get a little extensive. But in a nutshell, what these dependencies are doing is they're allowing us to make requests. That's what request is going to do. And then Tokyo and the async STD. Tokyo is really what enables you to make asynchronous requests. So like you don't necessarily have to do them one by one. You can do them on multiple threads, which is called parallel processing. But we're not going to dive a whole lot into that. But bring these in, make sure you get the versions correct because they do need to be compatible. And so when we go and hit these endpoints, you can see that we're getting a JSON payload back. So what you could do in Rust and actually in a lot of programming languages is you can actually serialize these JSON bodies into objects. And so if this looks at all like familiar to you after we've covered structs, then that's extremely astute, because what we can actually do is we can deserialize this JSON body into a struct object. And that's like one of the big uses for structs, you know? So we're gonna see that live. But in order to do that, in order to take a JSON payload and convert it into a Rust struct, we're also gonna add these bad boys here, which is called Saturday. And these are different Saturday libraries. And that's basically what this is going to enable us to do, is turn our JSON bodies into struct objects and be able to use them in our Rust app. Now, the last dependency I want to add, I mentioned this a little bit, is the ability to use environment variables in your application. We're going to use .env. So once you've got all these in there, go ahead and save it. And next time we do a cargo run or cargo build, these will all get pulled in. So let's go ahead and just take a look at that real quick. We'll CD into blockchain info app, and we'll just do cargo build. And we'll see all that stuff being imported right there. Awesome. So now while this is going on, I'm going to flip back to the app here. And for the first time, you guys are going to see how to use multiple Rust files in the same application. Like we're going to drive this thing from main RS, but we're going to have other Rust modules in our source folder that we're going to be able to use. So you're going to get a good taste of what that looks like. So to start, we're going to ignore main for now. And we're going to create some Rust files that are going to actually hold our structs that are going to process the information from those payloads. So the first one we hit.
I think I'm gonna stop here and do what I said. I'm gonna copy this stuff from the. Maybe I'll copy as I go along the videos, but I'm gonna do that off stream. And there's another one following up to this, which I don't remember if it's connected to this one, but I remember watching all of them. I'll probably watch these videos as well. Maybe I'll watch those on stream as well and copy this stuff, but next time my main goal is gonna be to actually start working on the chain data and going from the code that I have until I can, I'll think about what kind of data I wanna get out, what's possible to get out of the blockchain. And I'm probably gonna have to study the merge to proof of stake because I'm not sure. I think it's gonna happen soon. Probably. I don't remember, but I remember last time I saw that it was coming, and yeah. So I'm not sure how far they are with that. And I think what I'm gonna do at the beginning of each stream is I'm definitely gonna train this off stream as well. And I'm gonna do the Italian thing and the Vim training as well every single day until I get really good. So see you next time.